The main application of pure mathematics is to make you happy. Henrik Lenstra. I greet you all a sparkling morning. Today, we have gathered here for a state level webinar on graph decompositions and graph applications conducted by Department of Mathematics, Holy Cross College, Naharkoil. I am glad to welcome all of you who have joined here. I request all my dear friends to listen in such a way that others love to speak to you. Get ready for the great learning opportunity. Giving the first fruit of the day to the Lord is one of the valuable ways to show our love to God. With these sentiments in mind, let us invoke God's blessings on all of us through a prayer song. I welcome Miss Delphin, Miss Premika, Miss Asha Gold, and Miss Alfia Salu Shushmi of 2nd MSc Mathematics for a prayer song.
தாய் போல தேற்றி தந்தை போல ஆற்றி தோள் மீது சுமந்திடும் என் இயேசையா. தாய் போல தேற்றி தந்தை போல ஆற்றி தோள் மீது சுமந்திடும் என் இயேசையா. உம்மை போல புரிந்து கொள்ள யாரும் இல்லையே, உம்மை போல அரவணைக்க யாரும் இல்லையே, உம்மை போல புரிந்து கொள்ள யாரும் இல்லையே, உம்மை போல அரவணைக்க யாரும் இல்லையே. நீர் போதும் என் வாழ்விலே இயேசையா, நீர் போதும் என் வாழ்விலே, நீர் போதும் என் வாழ்விலே இயேசையா, நீர் போதும் என் வாழ்விலே. மலை போல துன்பம் என்னை சூழும் போது அதை பனி போல உருகிட செய்பவரே. மலை போல துன்பம் என்னை சூழும் போது அதை பனி போல உருகிட செய்பவரே. கண்மணி போல் என்னை காப்பவரே, உள்ளங்கையில் பொறிந்தென்னை நினைப்பவரே. கண்மணி போல் என்னை காப்பவரே, உள்ளங்கையில் பொறிந்தென்னை நினைப்பவரே. நீர் போதும் என் வாழ்விலே இயேசையா, நீர் போதும் என் வாழ்விலே, நீர் போதும் என் வாழ்விலே இயேசையா, நீர் போதும் என் வாழ்விலே.
Thank you, girls. A true welcome is never complete without warm words and warmer gestures. Here comes our beloved HOD, Dr. Kavita, Assistant Professor of Mathematics, Nagarkoil. She is more energetic, dedicated, and more friendly towards the students. Ma'am, I request you to extend a genial welcome.
Greetings to one and all. On behalf of the Department of Mathematics, SSF, Holy Cross College, Autonomous, Nagarkoil, I, Dr. S. Kavita, extend a very warm welcome for the state level webinar on graph decomposition and graph applications. First and foremost, I welcome Dr. Sister Annie Sobi, our principal, who always supports and encourages us to conduct enlightening sessions like this. Next, I welcome the resource person of today's webinar, Dr. Sitra Devi, is well-known researcher in graph theory. At present, she is working as assistant professor of mathematics in Sri Barasakti College for Women, Kuchalam. She has secured first rank and gold medal in her MPhil degree. At present, she is guiding four research scholars. She has presented many papers in various conferences and published more than 10 journals on graph theory, both nationally and internationally. She has served as a resource person in various colleges and organized national level workshop and seminar in her college. She has developed 8 modules as a subject expert for the MOOC course Graph Theory in Swayam platform. On behalf of myself and everyone present here, I accord you a very warm welcome, ma'am.
Thank you, ma'am.
A warm welcome to Dr. Ishwana, who is the resource person for the second section. I also welcome the faculty and students of other institutions and more my own colleagues and students. Welcome one and all.
Thank you, ma'am, for your benevolent welcome. A person who is always working for the betterment of the college and welfare of the students. It's none other than our principal, Sister Annie Perfect Sophie. Sister, we are waiting with full of ebullience to hear your precious words.
Respected special guests of today's state level webinar, Dr. Chitra Devi and Dr. Rizwana, faculty and students of other institutions and that of our own, a pleasant good morning to each one of you. This day has been gifted by God to have this state level webinar on graph decomposition and graph application today, organized by the Department of Mathematics Self-Financed. In this digital age, use of computers is increasing in human life. While this advancement is at its peak, most of the largely used applications, one way or other, use graph theory. Hence, graph theory has become a very large subject in the field of mathematics. Graphs are important because the way of expressing information in pictorial form and it attracts and it is explanatory. Graphs are not only related to the discipline of mathematics but also evokes interest in others. It is good that such a relevant topic has been chosen by the department as a title for this webinar today. In this context, we are very happy to have two eminent resource persons, namely Dr. Chitra Devi, Assistant Professor of Mathematics of the Barasakti College for Women, Kuchalam, and Dr. Rizwana, Assistant Professor of Mathematics, VHN, Senthil Kumar Nada College, Virudhunagar, to enlighten the participants connecting graph theory in mathematics with real life situations. Madam, on behalf of the management, I accord to both of you a very warm welcome. Thank you
Thank
for
you, ma'am.
sparing, thank you for sparing your valuable
Thank you,
time to
ma'am.
be with us to address our students and faculty and share your knowledge with them. I implore God's blessings on both of you, your family, and all your endeavors. I also take this opportunity to congratulate the faculty of the department, particularly Dr. Kavita, the HOD, and other faculty members, the organizing secretaries, Dr. Kavita and Ms. Safina, who have meticulously planned, prepared, and implemented in such a way that this day has come true. So I offer my warm felicitations to each one of the participants present here and to the resource persons I invoke God's blessings once again that this state level webinar be a fruitful one and benefit all the participants. Thank you.
Thank you, sister. Graph theory is the study of graphs, which are mathematical structures used to model pairwise relations between objects. Here comes our most successful resource person, Dr. P. Chitra Devi, Assistant Professor of Mathematics, Sri Parasakti College for Women, Kutralam, who is a person of distinct vision and hard work. She is here to share her knowledge on a glimpse on decomposition of graph with us. I welcome you, ma'am.
Thank you, ma'am. Is my PPT visible, ma'am?
Yes, ma'am. Yes,
Okay,
ma'am.
okay. Shall I start, ma'am?
Yes, ma'am.
Okay, thank you, ma'am. Good morning to everyone present here. I would like to present today on a glimpse on decomposition of graphs. The motivation behind today's talk is that the study of graph decomposition has become one of the most important topics in graph theory, and it is a most thrust area, and it plays an important role in the study of combinatorics of experimental designs. Where else can we apply this wonderful outcome? So let us see at the end of the slide what are else the applications. First, for today's session, I need some preliminaries from graph theory. Since third year and PG students are aware of graph theory, also first and second year students are here. So I will first explain what are all the basic preliminaries needed for the important session today. First, you must know what is meant by a graph. A graph is an ordered pair V of g, E of g, consisting of a non-empty set V of g of vertices and a set E of g disjoint from V of g of edges, together with an incidence function psi of g that associates with each edge of g an unordered pair of not necessarily distinct vertices of g. Actually, so apart from the definition, so let us see, a graph means it consists of a non-empty set of vertices. In the figure given below, I have given 4 vertices. You can see U, V, W and X. So these are the 4 vertices I have given for this graph. You can place these vertices at any, I have placed in some order. You can place in any order as you like. Then it consists of a set E of g of edges. The edges are nothing but the links between the vertices. For example, here E is an edge between U and B. It means that there is a link between U and B. The next edge I had given is EF. So this denotes that there is a link between V and W, the vertex V and vertex W. I have named only 2 edges. There is an edge opposite to E, that is XW. There is an edge opposite to F, that is UX. And there are 2 edges in the diagonals, that is UW as well as VX. So totally there are 6 edges and 4 vertices in this graph. The number of vertices and edges in G are denoted by, are called the order and size of G. Number of vertices is the order of G. Therefore, the order of this graph is 1, 2, 3, 4, 4. Number of vertices. The number of edges is called the size of G, and hence the size of this graph is, already I have told there are 6 edges. So size is 6. So now let us see the next definition. If E is an edge and U and V are vertices such that psi G of E equal to UV, meaning that E links U and V, then we say that E is set to join U and V, and the vertices U and V are called the ends of E. The ends of an edge are said to be incident with the edge and vice versa. In the graph, you can see that this E links U and V. So we say that E joins U and V. Also, we can see that the edge is nothing but U and V. Also, we say when we are talking about an edge and one of its ends, we say that the edge is incident with the vertex and vice versa. That is, the vertex is incident with the edge. Okay, then we say that two vertices are adjacent if they have a two vertices are adjacent if they are the ends of a same edge. So for example, U and V are the ends of the edge E. So we say that U and V are adjacent. Similarly, you can tell that two edges are adjacent. So now you can see here edge E and edge F has a common end. V is a common end for both the edge E and F. Now we say that the edges E and F are adjacent. Okay. Two vertices which are incident with a common edge are adjacent, as are two edges which are incident with a common vertex. So two distinct adjacent vertices are called as neighbors. For example, in that graph, U and V are neighbors. Now let us come to the degree of a vertex. So now we have seen what is meant by neighbors. So for each vertex, we associate a concept degree. The degree is nothing but the number of its neighbors. You had to count a vertex neighbors, and that number gives the degree of that vertex. A vertex of degree 0 is called an isolated vertex because it will not be associated to, if it is of degree 0 means it will be alone present here. It will not be adjacent to any of the vertices. It will not have a neighbor. So it remains isolated. So it gets the same name. It is called isolated vertex. So you can see here U has three neighbors, V, W, X. So degree of U is 3. Similarly, you can find the degrees of all the other vertices. Okay. So now let us come to the important concept, a complete graph. Now we have seen what is meant by a graph. Okay, you know what is meant by a graph now. So one more concept I didn't tell. So you can also link a vertex with itself. You can give a link between a vertex to itself. It will form a loop. So this is called a loop. Similarly, between two vertices, you can give more than one links. That is, here I have given an edge E. You can also give some other edge G between U and V. So such edges are called as multiple edges. So a graph that doesn't have multiple edges as well as loop, such structures are avoided in simple graph. Such graph is called a simple graph. In simple graph, there is no multiple edges and there is no loop. Okay, so a simple graph in which any two distinct vertices are adjacent is called a complete graph. For example, so in this graph, you can take any two distinct vertices. For example, you know that U and V are adjacent. Similarly, U and W are also adjacent. There is a link between them. U and X is adjacent. Suppose take some other vertex, V as well as E. Yes, sorry, X. Now V and X are also adjacent. So in this graph, any two distinct vertices are adjacent and they are also simple because there is no multiple edges and there is no loop. So such a graph is called a complete graph. A complete graph on n vertices is denoted by k suffix n. So this graph is nothing but the number of vertices is 4. So this graph is k4. Okay. A complete graph is a simple graph in which any two distinct vertices are adjacent. Okay, so next definition is bipartite graph. A bipartite graph is a graph whose vertex set can be partitioned into two subsets x and y such that every edge has one end in x and one end in y. What is the meaning? So the vertex set can be partitioned into two sets. So x, y. In between the vertices of x, there doesn't exist an edge. There is no connection link between the vertices of x, and similarly there is no links between the vertices of y. If an edge exists in this graph, it links only a vertex of x to a vertex of y. Such a graph is called a bipartite graph. So if a graph is bipartite and it is simple and every vertex in x is joined to every vertex in y, then such a graph G is called a complete bipartite graph. That is, in addition to this, you can we have told that in a bipartite graph, if there exists an edge, it joins an end of x to an end of y. Okay, So if every vertex of X is joined to every vertex in Y, it becomes somewhat full. That graph is called as complete bipartite graph. So if number of vertices in X is M and number of vertices in Y is N, then the complete bipartite graph is denoted by K suffix M comma N. If M or N are replaced by 1, then K1 comma N is called a star. Actually, the structure resembles a star, so it gets the same name. Okay, a path is, now let us see the next definition. A path. Path means it's a simple graph whose vertices can be arranged in a linear sequence in such a way that two vertices are adjacent if they are consecutive in the sequence and are non-adjacent otherwise. Actually, a path means the vertices can be arranged in a linear sequence. For example, you can think as a straight line, and two vertices are adjacent if they are consecutive. That is, if I am arranging the vertices as 1, 2, 3, etc. up to n, 1 will be adjacent to 2. So there will be a link between 1 and 2. 2 will be adjacent to 3. So there will be a link between 2 and 3, etc. up to, it will continue up to n minus 1 is will be adjacent to n. So it forms a linear sequence, and it also resembles a path. So it is called a path. Next, cycle means, one second, here. Okay. Cycle means it must contain at least 3 vertices, and it is a simple graph whose vertices can be arranged in a cyclic sequence in such a way that two vertices are adjacent if they are consecutive in the sequence, they are non-adjacent otherwise. So same thing, what we'll do is we'll join n with 1. We will identify n with 1 in the linear sequence. So it forms a cyclic sequence, and two consecutive vertices, they are adjacent. So it forms a cycle. It resembles a circle, actually, circle. Okay, that is called cycle. For example, in the previous figure, okay, so the graph I have given to you. So see here, you can see you can mean this as a path. U to V, then V to W, W to X. Only this one. 1, 2, 3. If you are considering these 3 edges with the corresponding ends, then it forms a path. So if I am also joining this XU edge also, then it forms a cycle. So these are the examples of cycles and path. Okay. Okay, next, you can also count the number of edges that are available in path or cycle. That number of edges gives the length of the path or length of the cycle. A path with n vertices is denoted by Pn, and a cycle with n vertices is denoted by Cn. Actually, it depends on book. In some book, a path with n edges will be considered as Pn. But for our session today, we consider Pn as a path on n vertices, Cn as a path on cycle on n vertices. Okay, so next one is a subgraph. A subgraph height of a graph G is a graph such that the vertex set is a vertex set of height is a subset of vertex set of G, and edge set of edge is a subset of edge set of G. Both vertex set and edge set are subsets of the corresponding graph G. Okay, so if suppose V of H is equal to V of G, then such subgraphs has a special name, spanning subgraph. A spanning subgraph of a graph G is a subgraph obtained by edge deletions only. That is, there is nothing to do with vertex. The vertex is full as the vertex set of G. In other words, a subgraph whose vertex set is the entire vertex set of G. Okay, similarly, you can think of spanning paths and spanning cycle. Spanning paths are called as Hamilton paths. Spanning cycles are called as Hamilton cycles. A graph that contains a Hamilton cycle is called a Hamiltonian graph. Okay, so now let us come to the important thing, decomposition of graphs. Now we have entered into the research. Okay, decomposition means it's a collection of subgraphs G1, G2, Gn of the original graph G. So it is called a decomposition of G if each GI has no isolated vertices. There should not be isolated vertices in these subgraphs, and the edge sets of the graphs G1, G2, etc. Gn, that is E of G1, E of G2, etc. E of Gn, forms a partition of the edge set of G means E of G, forms a partition of E of G. That is, we know that partition means union must be E of G must be equal to E of G1 union E of G2 union E of Gn, and EGI must be non-empty. That is, we have told that it has no isolated vertices. Okay. And one more thing is the edges. Actually, every edge of G must be in exactly one edge of Gn. That is, I will say partition means intersection is non-empty. That is, it should not have a common edge. An edge should not be present in no edge should be present in more than two graphs. That is, every edge of G is present in exactly one subgraph GA. So now let us see an example for decomposition. The same graph I have taken K4. Now K4 can be decomposed into two parts. See here, this structure 1, 2, 3. That is this one. This
Ma'am?
one. Yes, ma'am.
Ma'am, can you put in slideshow, ma'am?
Slideshow. Yes, ma'am. Yes. Sorry, I forgot actually. Okay. Thank you, ma'am. Thank you for
Okay, ma'am.
reminding. Okay, ma'am. Okay, ma'am. So students, listen here. Now this K4 can be decomposed into, see here, this is a path P4. So this one. And what are the left out edges? These are the left out edges. So this graph, this subgraph also forms a P4. See here, 1, 2, 3. This is also P4. So P4 means path on 4 vertices. I have told from the start. Pn means path on n vertices. So this is also a P4 and this is also a P4. Here both subgraphs are same. So for that we have the next definition. If we are seeing a decomposition of graphs and if each GI is isomorphic to H for all I equal to 1 to n, for some subgraph H of G, then the decomposition is called an isomorphic decomposition of G. So in this case, we say that G is H decomposable. So this K4 is P4 decomposable. It is decomposed into two copies of P4. Okay. So the next one, path decomposition of graphs. Why we are learning, why we want to study path decomposition of graphs? Actually, it is of interest because computing path decompositions turns out to be an important problem in VLSI design. What is VLSI design? Very large scale integration. It is a process of creating an integrated circuit by combining thousands of transistors into a single chip. Actually, for creating chips, there should not be overlapping. So the path decomposition, actually we will decompose in such a way that the overlapping doesn't happen. So this path decomposition plays an important role in VLSI design. So you have so not only path means general paths, you can start from P4 onwards, P4, P5, Pn general. You can start. It is very important. It is a very thrust area. Okay, the first problem due to Holler in the year 1981. So the problem was, given a graph G, is there a H decomposition of G? That is, given a graph G and a subgraph H of G, the question is whether there exists a H decomposition of G. Actually, the problem remained unsolved, and in the year 1997, Dorr and Dorsey gave the theorem that if H has at least 3 edges, then the problem of deciding if a graph G has a H decomposition is NP complete. Actually, till now there doesn't exist a polynomial time algorithm, that is to solve whether a graph G is H decomposable. If H has at least 3 edges, then what about a graph with 2 edges? Now we are seeing path decomposition. So what about P3? Okay, P3 means the path on 3 vertices. So it will have 2 edges. So our instinct says that if a graph has even number of edges, then it must be P3 decomposable. Our instinct will tell that, but it is true and it has been proved. Okay, every connected graph with an even number of edges has a P3 decomposition. For this, they will be using orientation technique. Okay, so obviously our next question will be, we have completed P3, so can we think of P4 decomposition? So this will be the next question. So P4 decomposition means number of edges in the graph is 3. So our question will be, if a graph has multiple of 3 edges, then it should be P4 decomposable. This will be our instinct, but that is not true. You can see a counter example. The following is an example of a two connected graph with 12 edges, which is not P4 decomposable. See here. So you can see here, I have chosen the green edges first. If I am taking these three as a P4, this line as a P4, that is this one, this one, this one, obviously in the next choosing, you will be choosing like this way or this way. One of the edges will be left out, so P4 decomposition is not possible. So optimally, I have taken this one, this one. So next we will be choosing this one, and if you are choosing this one, then the next selection, this edge will be left out or this edge will be left out. So I have taken this one, 1, 2, 3. So you can choose this, but what we have arrived at, so here we have got a K3, not a P4. So in whatever ways you try for this graph, you will not get a P4 decomposition. This graph is not P4 decomposable, but it has multiple of 3 edges. Okay, then it is worth to study P4 decomposition in a graph, and you can characterize when it is P4 decomposable. So that is what I am going to do today. So I have 3 proofs today, and I will give 3 proof techniques also. The first proof technique is I am going to use number theoretic concept for decomposition of graph. For this next one is I am going to use induction method, and the third one I am going to use is building blocks method. So 3 methods I have opted, but there are lots and lots of methods for decomposition, decomposing a graph. So the main thing will be, actually they will be using Latin square, partial Latin square, etc. Even we have used in our proof, but today I'm going to touch only the 3 methods: using number theory, using induction, and using building blocks method. Okay, so some smaller structures which are P4 decomposable will be discussed first, and then I will go into the theorem. So for example, K2, 3 complete bipartite graph with 2 vertices in one partite set and 3 vertices in other partite set. This is P4 decomposable. I have given a P4 decomposition. This dotted lines, this denote a P4, and similarly the dark lines, this denote a P4. So it is P4 decomposable. Similarly, K3, 3, it is also P4 decomposable. So see, you can see the different colors. These denotes P4. So pink color, this green color as well as blue color denotes 3 copies of P4. So it is P4 decomposable. One more thing to keep in mind is number of edges in Km, N is Mn. Here you will have 6 edges. Here you will have 9 edges. Obviously, both are multiple of 3, and it is P4 decomposable. So the next question will be whether general Kmn is P4 decomposable. Yes, it is P4 decomposable. So let us use the number theoretic concept. Okay, Kmn is P4 decomposable if and only if m is greater than or equal to 2, n is greater than or equal to 2, and mn is congruent to 0 mod 3. Number of edges is a multiple of 3, that is given there. Okay, so let us see the proof. First, we know that the number of edges in Kmn is nothing but m into n. Okay, suppose Kmn is P4 decomposable. Automatically, the number of edges must be a multiple of 3, because we are breaking into 3 edges. So obviously, mn must be congruent to 0 mod 3. And if m is equal to 1, it will become a star. It is not P4 decomposable. So automatically, m and n must be at least 2. So necessary part is completed. Now we want to prove only sufficiency. Okay. So without before that, so the sufficiency means we are going to assume these things: m greater than or equal to 2, n greater than or equal to 2, and mn congruent to 0 mod 3. So now we had to prove, give a P4 decomposition for this Km, n. So we have assumed that mn congruent to 0 mod 3. So 3 divides mn. Since 3 is prime, 3 divides m or 3 divides n. So without loss of generality, let us assume that 3 divides m, that is m is multiple of 3, that is 3r. Now, here only we are going to use number theoretic concept. We have a theorem that if n is any integer and GCD of a comma b divides n, then n is equal to ax plus by has a solution. We have this theorem. So using that, now n can be written as n is equal to 2s plus 3t, because GCD of 2, 3 is equal to 1, and that 1 divides n. So this will have a solution. So for some s and t, this will exist, n equal to 2s plus 3t. and S is greater than or equal to 0 and T is greater than or equal to 0. Now, using this thing, how we are going to decompose? We can see in the next figure. Actually, we are going to decompose K suffix M comma N. So I have given this figure for K M comma N, but in my own way. See here we have told that M is equal to 3R. So I have split it into R copies of 3 vertices. So first copy with 3 vertices, second copy with 3 vertices, and rth copy with 3 vertices. Similarly, right hand side we have told that N can be written in the form 2S plus 3T. So 2S means S copies of 2 vertices and 3T means T copies of 3 vertices. I have split it this into simplest form. Okay, so I have set it like this. Now complete bipartite graph means every vertex from this set must be adjacent to every vertex from to this set. Okay, so now I am taking on set. So if I am taking this set, first set with this one, this pink set, then every vertex from this must be adjacent to every vertex in this, implies this is k3 comma 2. This is isomorphic to k2 comma 3. So this forms a k2 comma 3. One copy of k2 comma 3. So similarly, when this is adjacent to the second one, it forms another copy of k2 comma 3. When this is adjacent to this the set, it forms s copies of k2 comma 3 for this one set. Similarly, for the second set, you will have another s copies of k2 comma 3. For this rth set, you will get another copies of k2 comma 3. Another s copies of k2 comma 3. Overall, we get rs copies of k2 comma 3. Similarly, so we have completed the first part. So let us come to the lower part. Here you have 3 vertices here and 3 vertices here. So we will have a k3 comma 3 here. So totally we will have for this set t copies of k3 comma 3. So for the second we will have another t copies of k3 comma 3, and for the rth set we will have another copies of k3 comma 3. Overall we will have rt copies of k3 comma 3. So that is given in the proof now. Okay, so now come to this line. Then km comma n can be decomposed into rs copies of k2 comma 3 and rt copies of k3 comma 3. Previously we have told that k2 comma 3 is p4 decomposable and also k3 comma 3 is p4 decomposable through a diagram. So now overall kmn is p4 decomposable. So we have proved this theorem. So in general, complete bipartite graph is P4 decomposable if m greater than or equal, if and only if m is at least 2, n is at least 2, and 3 divides mn. Okay, come to the next proof. This is not with the P4 decomposition. This is with the general decomposition. Okay, H decomposition. If Kr and Kr comma R are H decomposable, then automatically the complete graph Knr is H decomposable for any positive integer n. So this we are going to prove by the method of mathematical induction. So let us prove by mathematical induction on n. So suppose n is equal to 1 means knr is nothing but kr. By assumption, it is already H decomposable. Okay, so for base step we have proved. Now assume that the lemma is true for n equal to m minus 1, which is greater than or equal to 1. So by our assumption, k suffix m minus 1 into r is H decomposable. This is our assumption. So now we have to prove the lemma for n equal to m. Now k we can write mr as m minus 1 into r plus r. So minus r plus r gets cancelled. So it is mr. Okay. So now this can be okay. So now what we can do is kmr can be splitted into two sets, m minus 1 into r in one side, r in another side, r vertices in another side, and here it forms a complete graph. This side it also forms a complete graph. See here, I have taken m minus 1 into r vertices here. I have partitions in some other way. You don't think about that. M minus 1 into r vertices in this side and r vertices in the other side. Actually, we have taken complete graph. So every vertices inside this will be adjacent to each other. So overall, we'll get a complete graph k suffix m minus 1 into r. That is this set, this graph. So we are splitting that. Here you will have a KR inside these vertices. So I am taking that also alone. Then there are also edges between every vertex from here to every vertex in this set. So that we will bring in terms of complete bipartite graph. I have denoted double line means it denotes a complete bipartite graph from that set to the this set, from the to the right hand side set. Okay. Here also we are having R vertices. Here also we are having R vertices. So it forms K R comma R. So totally we have m minus 1 sets of R copies of R vertices. So we get m minus 1 copies of K R comma R. So original graph is divided into 3 sets. That is a graph K m minus 1 into R, that is this side, a graph KR, and m minus 1 copies of K R comma R. Okay, that is given here. Edge set of K m minus 1 into R plus R, that is K m R. I have written that only here. It can be written as edge set of K m minus 1 into R union edge set of KR union m minus 1 copies of edge set of KR comma R. By assumption, KR and KR comma R are H decomposable. So this part completely becomes H decomposable. By our induction assumption, K m minus 1 into R is also P4 decomposable. So the whole graph becomes a P4, sorry, not P4, H decomposable. Therefore, by induction hypothesis and by our assumption, Km into R is H decomposable. So the theorem is proved. So this seems to be easy for you when you are looking at the proof, but to find this method, it is really difficult. You have to think in which way we have to prove the theorem. Okay, so this we have used induction hypothesis. Now let us prove that the complete graph is P4 decomposable. When which condition? We are characterizing complete graphs to be P4 decomposable in the next theorem. Okay, before that you need a theorem due to Lucas. The graph K suffix 2n plus 1, that is graph on complete graph on odd vertices, can be decomposed into n Hamilton cycles for every natural number n. This is very strong theorem, and to prove this proof is very tedious, but it is used in many places. In many places this theorem will help you to decompose. The graph on odd vertices can be decomposed into Hamilton cycles. Since it is 2n plus 1, we get n copies of Hamilton cycles. Okay. So next one, K6 is P4 decomposable. Actually, we are going to use this in the next theorem. So previously, I have shown you that this graph is P4 decomposable. See here, you can see 5 copies of P4 here. Black, red, yellow, blue, and green. Actually, it is P4 decomposable. I have decomposed and shown you. So now let us go into the next theorem. Kn is P4 decomposable if and only if this n must be greater than 3. If it is 1 means also we'll get K1, it is not P4 decomposable. 2 means it is K2, it is also not P4 decomposable. K3 means you will get a cycle. So it is also not P4 decomposable. So, and the second condition is n is incongruent to 2 mod 3. Okay, so now let us come into the proof. So necessary part is easy. So suppose assume that Kn is P4 decomposable. Okay, yeah. Now what I have told, that is given in the first line. For n less than or equal to 3, it is not P4 decomposable. Now assume that Kn is P4 decomposable. So automatically the number of edges must be a multiple of 3. Number of edges in Kn is n into n minus 1 by 2, because any two distinct vertices are adjacent. So out of n vertices, every 2 we get an edge. So totally we will get nc2, that is n into n minus 1 by 2 edges. Okay, n minus, this must be a multiple of 3. If n is congruent to 2 mod 3, then automatically n will also be not a multiple of 3, and n minus 1 also will not be a multiple of 3. Totally, cardinality of E of Kn will not be a multiple of 3. So, this case is not allowed. Okay, so let us come to n congruent to 0 mod 3. Obviously, n will be a multiple of 3. Okay, it will hold, and n is congruent to 1 mod 3 means also n minus 1 will be a multiple of 3. So next two cases holds. Only n is congruent to 0, 2 mod 3 doesn't hold here. Okay, so n is incongruent to 2 mod 3. So necessary condition is obvious. We have proved. Now let us prove the sufficiency. So we assume that n is greater than 3 and n is incongruent to 2 mod 3. Okay, here we have reminded that K4 is P4 decomposable because we'll be using later. So I have reminded here. Okay. Okay, see here, we are going to prove the sufficiency condition. There arises two cases. See here, we have given n is incongruent to 2 mod 3. So two cases means first case is n is congruent to 0 mod 3 or n is congruent to 1 mod 3. You have to discuss the two cases. In the two cases, you have to give P4 decomposition for Kn. So generally, let us assume we have told that n is greater than 3. When n is equal to 4, we know that K4 is P4 decomposable. Already I had shown previously. So what about K5? K5 is not included because that n is congruent to 2 mod 3. If n is 5, then n is congruent to 2 mod 3, so it is not allowed. So automatically n is greater than or equal to 6. Let us assume this case. For 4 we have proved. Then in remaining cases n is greater than or equal to 6. So keep in mind. So case 1, n is congruent to 0 mod 3. So previously Lucas stated that when n is odd, Kn is decomposable into Hamilton cycle Cn and n is multiple of 3. So a cycle, see here, n is greater than or equal to 6 we have told, and suppose assume that n is equal to 6. So we'll get C6. C6 can be decomposed into 2 copies of P4. So for example, you think 1, 2, 3, 4, 5, 6, 6 vertices. Okay. So 1 to 2, 2 to 3, 3 to 4. This forms a P4. Similarly, 4 to 5, 5 to 6, 6 to 1. This forms a P4. So C6 can be divided into 2 copies of P4. Similarly, C9 or C12, multiple of 3. Any multiples of 3 can be divided into copies of P4. That is what given here. When n is odd, Kn is decomposable into Hamilton cycle Cn. So since n is congruent to 0 mod 3, it can be decomposed into copies of P4. So odd case we have completed. So let us come to even case. Suppose n is even. So n must be equal to, n is even means n is multiple of 2. Already n is multiple of 3 here. So totally n is multiple of 6. So we can assume that n is equal to 6 into r. So previous only we have told that K6 is P4 decomposable. Now what about K6R? So we are going to use that techniques we have used previously. 6R can be written as 6 into R minus 1 plus 6. 6 into R minus 1 plus 6. So since this is complete graph, it can be splitted into K6 into R minus 1 and 6 vertices are in the right hand side. So one K6 we will be getting and complete bipartite graphs between them. Okay, complete bipartite graph means we have 6 into R minus 1 means R minus 1 copies of 6 vertices here. Each set contains 6 vertices. In right hand side also there are 6 vertices. So between them there will be R minus 1 copies of K6, 6, complete bipartite graph K6. So that is what I have given here. I don't think I have given the diagram for that. It resembles exactly the same as previous. So only I have not given the figure. Okay, now K6, 6 means 6 into 6. It's a multiple of 3. Already we have shown that Kmn is P4 decomposable if and only if Mn is a multiple of 3. So this is P4 decomposable. This is P4 decomposable. Also, we have shown that K6 is P4 decomposable. Now, if you are using induction, base step is here. If you are using induction, this will also be P4 decomposable. So K6R is P4 decomposable. By induction, you can prove this one. Okay, now come to the next one. N is congruent to 1 mod 3. So you can write n as multiple of 3 plus 1. So n is equal to 3k plus 1. If you are putting k equal to 1, it becomes k4. We know that it is P4 decomposable. Assume that this k is greater than 1. Now, as we have done previously, we can write it in a simple way. See here, e of k suffix 3k plus 1 can be written as 3 into k minus 1 plus 4. See here, 3k plus 1 can be written as 3 into k minus 1 plus 4. So now we can split it into two copies of complete graphs, that is E suffix k, E of k suffix 3 into k minus 1 union E of k4 union, then a complete bipartite graph comes, that is k minus 1 copies of k3 comma 4, k3 comma 4, and we know that 3 into 4, it is a multiple of 3. So therefore, these are all P4 decomposable. K3 comma 4, every copies are P4 decomposable. This is P4 decomposable. And if you are using induction here, so not induction, sorry, no, this is not, here we are not using induction. This is a complete graph with, what is this, multiple of 3 edges. Case 1 is, we have proved that when n is multiple of 3, kn is P4 decomposable. We have proved here. So by using case 1, this also becomes P4 decomposable. So totally it is P4 decomposable. Therefore, k suffix 3k plus 1 is also P4 decomposable. This completes the proof of the theorem. Actually, we are using case 1 here. So here we have used induction method. Okay, so the last proof I am going to deal with, that is, let G be a complete tripartite graph, k suffix m1, m2, m3. Now we have to prove that G is P4 decomposable if and only if the number of edges, that is Q of G means number of edges of G is a multiple of 3 and number of edges is greater than 3. So this is the condition. Actually, necessary part is obvious only. As previous, we can prove this one, because if number of edges is 3 means that forms a cycle. This forms K3, so it is not P4 decomposable. So number of edges must be greater than 3, and number of edges is multiple of 3 means only you can decompose into P4. So this condition is necessary condition and obvious condition. So necessary condition is obvious, and you had to prove only sufficiency. For sufficiency, we know that the number of edges in k suffix m1, m2, m3 is, what is that? You have 3 copies of partite sets, partites, m1, m2, m3, and every vertex is adjacent to all the other vertices in the other partite sets. So 1 second, I'll give this one. See, this is 3 set of partite sets. So there will be adjacencies from here to here. There will be a complete bipartite here. Here there will be a complete bipartite graph, and here there will be a complete bipartite graph. So number of edges will be number of edges in this into the number of vertices. So here there is a complete bipartite graph. So if m1 is the vertex here, number of vertices here, and m2 is the number of vertices here. So for this complete bipartite graph, the number of edges will be m1, m2. Similarly, here the number of edges will be m2, m3. And here the number of edges will be m3, m1. Totally, the number of edges will be m1, m2 plus m2, m3 plus m3, m1. So now we have assumed that this is multiple of 3. So this is multiple of 3 means there are 3 possibilities. First one is, if everything is if mi is congruent to 1 mod 3 for all I, that is, this m1 is multiple of 3 plus 1, that is 3a plus 1. m2 is also 3b, some 3b plus 1, and m3 is some 3c plus 1. So overall, if you are multiplying, here we will get a multiple of 3 plus 1. Similarly, here also you will be getting a multiple of 3 plus 1. Here also you will be getting a multiple of 3 plus 1. So in these 3 terms, you will be having 1 plus 1 plus 1. That also becomes 3. Overall, it will be a multiple of 3. So the first case will be okay. So then second case is, if mi is congruent to 2 mod 3 for all I. So 2 mod 3 means when you are multiplying here, 2 mod 3 means it will be of the form 3a plus 2, 3b plus 2, 3c plus 2. When you are multiplying, you will be getting 3a plus 2 into 3b plus 2 means you will be getting 4. So multiple of 3 plus 4. Similarly, here also you will be getting multiple of 3 plus 4. Similarly, here also you will be getting multiple of 3 plus 4. Totally multiple of 3 plus 12. That is also a multiple of 3. So the last case, mi will be congruent to 0 mod 3 for at least 2i is enough, not for 3 also. See here, suppose m1 and m3 are multiple of 3. Let us assume like that without loss of generality. So then m1 is multiple of 3 means this term becomes multiple of 3. Also we have assumed that m2 is multiple of 3. So this term also becomes multiple of 3. Here once again you are having m1. So this also becomes multiple of 3. Overall, Q of G will be congruent to 0 mod 3. So when Q of G is congruent to 0 mod 3, there are only 3 possibilities. These are the 3 possibilities. Therefore, in these 3 possibilities, you get 3 cases, and in these 3 cases, you have to show that G is, that is case K, M1, M2, M3 is P4 decomposable. That is what you had to prove. So let us assume that M1 is some 3A plus 1, and M2 is 3B plus 1, and M3 is 3C plus 1, where A, B, C are integers. Okay. So now our K suffix M1, M2, M3 can be split up into 2 subgraphs as below. See here. Here I am having 3A plus 1. This is one set. Here 3B plus 1 vertex I have placed here, 3B plus 1, 3C plus 1. See here, only I have splitted these two. இதெல்லாம் ஃபுல்லா பாருங்க, 3B plus 1, 3C plus 1 ஃபுல்லா பாருங்க. இதை மட்டும் ரெண்டா ஸ்பிளிட் பண்ணிக்கோங்க. Here 3A and here 1. Now this 3A will also be adjacent to all vertices in 3B plus 1 and all vertices in 3C plus 1. Also, this one vertex will be adjacent to all vertices in 3B plus 1 plus all vertices in 3C plus 1. Also, complete tripartite graphங்கிறனால இந்த ரெண்டு செட்டுக்கு இடையில ஒரு complete bipartite graph இருக்கும். இங்க உள்ள எல்லா verticesம் இங்க உள்ள எல்லா vertices கூடயும் adjacent ஆகும்போது இதுல ஒரு complete bipartite graph வரும். So, இது நான் வந்து எந்த ஸ்ட்ரக்சர்ல கொடுத்திருக்கேன்னா double line means there is a complete bipartite graph. அதுதான் அதோட மீனிங். இந்த double line கொடுத்தாலே அந்த செட்ல இருந்து இந்த செட்டுக்கு ஒரு கம்ப்ளீட் பைபார்டைட் கிராஃப் இருக்குன்னு அர்த்தம். சரியா? சோ இதுல நான் வந்து அந்த கம்ப்ளீட் பைபார்டைட் சொல்லி இருக்கிறதுல ஐ ஹவ் given ரெட் லைன்ஸ் ஹியர். இந்த ரெண்டு பிளேஸ்ல என்ன கொடுத்திருக்கேன்? ரெட் லைன்ஸ் கொடுத்திருக்கேன். இந்த ரெட் லைன்ஸை வந்து மட்டும் நீங்க வியூ பண்ணி பாருங்க. இந்த பக்கம் 3A வெர்டிசஸ் இருக்கு, இங்க 3C plus 1 இருக்கு, இங்க 3B plus 1 இருக்கு. இதுக்குள்ள எந்த அட்ஜசன்சியுமே இல்ல. அப்ப நான் இந்த மொத்தத்தையும் சேர்த்து ஒரு செட்டுக்குள்ள தூக்கி போட்டுடலாம். அதுல எவ்வளவு இருக்கு? 3B plus 1 plus 3C plus 1 ஒரு பார்டைட் செட்ல இருக்கு. இன்னொரு பார்டைட் செட்ல என்ன இருக்கு? 3A மட்டும். அப்போ this is nothing but complete bipartite graph 3A, 3B plus 1 plus 3C plus 1. இதை தவிர ரிமைனிங் எல்லா வெர்டிசஸையும் பாத்தீங்கன்னா அது ஒரு கம்ப்ளீட் ட்ரைபார்டைட் கிராஃப் ஃபார்ம் பண்ணும். இங்க ஒரு வெர்டெக்ஸ் இருக்கு, இங்க 3B plus 1 இருக்கு, இங்க 3C plus 1 இருக்கு. இதுக்குள்ளேயும் adjacency இருக்கு. So this is nothing but union edge set of K suffix 1, 1 மட்டும்தான் இருக்கு. 3A முடிச்சிட்டோம் நம்ம. 3B plus 1, 3C plus 1. நமக்கு தெரியும் இது வந்து complete bipartite graph. இதுல number of edgesங்கிறது this into this தான். இதை மல்டிப்ளை பண்ணீங்கன்னா அங்க 3 இருக்கு. அதனால டோட்டலா எல்லாம் மல்டிபிள் ஆஃப் 3 வந்துரும். So நம்ம அந்த ஃபர்ஸ்ட் தியரம் KMN is P4 decomposable if and only if MN is congruent to 0 mod 3 யூஸ் பண்ணோம் பாத்தீங்களா? அதை யூஸ் பண்ணோம்னா இது ஆட்டோமேட்டிக்கா P4 decomposable ஆயிரும். சரியா? அப்போ நீ இதை பத்தி கவலைப்பட வேண்டாம். நீ எதை மட்டும் கவலைப்பட்டா போதும், இதை மட்டும் இப்ப இது P4 decomposableான்னு பார்க்கணும். சோ இதுதான் பில்டிங் பிளாக்ஸ் மெத்தட். பிளாக்கா வச்சு கெட்டி கெட்டி மேல கொண்டு போறது மாதிரி, அது ரிவர்ஸ்ல. புரியுதா? திஸ் இஸ் த மெத்தட் ஆஃப் பில்டிங் பிளாக்ஸ். சோ ஓகே, செகண்ட் வந்து என்னன்னா இதை மட்டும் இப்ப நம்ம வியூ பண்ணா போதும். இப்ப நான் என்ன பண்ண போறேன்னா இப்போ இங்க 3A plus 1 நான் பிரிச்சது மாதிரி இங்க நான் எதை ஸ்பிளிட் பண்ண போறேன்னா ஐ எம் கோயிங் டு ஸ்பிளிட் 3B plus 1. So you can see in the next figure. So இங்க 3B plus 1 ஆல்ரெடி இங்க 3A எடுத்துட்டோம். அதனால 1 மட்டும் தான் இங்க இருக்கு. இங்க 3C plus 1 இருக்கு. இப்போ இதை நான் ரெண்டா பிரிக்க போறேன். 3B adjacent to this one vertex and 3C plus 1 vertex. Similarly, this 1 is adjacent to this one vertex and this 1 is adjacent to 3C plus 1 vertex. Also, in between this one vertex and 3C plus 1, there is a complete bipartite graph. This is the structure. இப்போ K suffix 1, 3B plus 1, 3C plus 1. இப்போ நான் என்ன பண்ண போறேன்னா இந்த ரெட் எட்ஜஸ் மட்டும் நான் தனியா எடுத்துற போறேன். அந்த ரெட் எட்ஜஸ் இல்ல, அந்த கிராஃபே நான் பிரிச்சு தனியா எடுக்க போறேன். That is nothing but K suffix 3B, இங்க வந்து உள்ள லிங்க் இல்ல, ரெட் கலர் லைன் இதுக்குள்ள வரல. அதனால இதை நான் சேர்த்து ஒரே செட் எடுத்துற போறேன். 1 plus 3C plus 1. T of K suffix 3B, 1 plus 3C plus 1 union மீதி எல்லாத்தையும் எடுக்க போறேன். இங்க 1 இருக்கு, இங்க 1 இருக்கு, இங்க 3C plus 1. K suffix 1, 1, 3C plus 1. So இப்ப இதை பார்த்துட்டீங்கன்னா ப்ரீவியஸா நம்ம யூஸ் பண்ண தியரம் தான் KMN is P4 KM, N is P4 decomposable if and only if Mn is the multiple of 3. இப்போ இந்த M-ஐயும் N-ஐயும் மல்டிப்ளை பண்ணீங்கன்னா இங்க 3 இருக்கிறனால multiple of 3 வந்துரும். So this graph is P4 decomposable. So இதை பத்தி நம்ம கவலைப்பட வேண்டாம். You have to worry only about this one. ஓகே, இப்போ நமக்கு வந்து லாஸ்டா இதை மட்டும் பார்த்தா போதும். ஸோ இப்போ கே சஃபிக்ஸ் 1 1 3c plus 1 எப்படி நம்ம பிரிக்கிறது அந்த கிராஃபை. ஸோ யூ கேன் see here நான் எப்படி பிரிச்சிருக்கேன்னா, ஸோ சப்போஸ் c is 1 ரெண்டு கேஸா பிரிப்பேன் நான் இங்க சப் கேஸா. சப்போஸ் c is 1, சப்போஸ் c is greater than 1. c equal to 1 இது என்ன வருது பாருங்க, k suffix 1 1 4 ஒரே கிராஃப்ல முடிஞ்சிருது. ஓகே, k suffix 1 1 4 நான் பின்னாடி சொல்லியிருப்பேன் k suffix 1 1 4 is p4 decomposable காமிச்சிருப்பேன். ஓகேயா, ஸோ இப்போ k suffix 1 1 3c plus 1 பத்தி கவலைப்படணும் எப்போ c greater than 1. ஓகே, சப்போஸ் assume that c is greater than 1. அப்ப நான் இதை எப்படி பிரிக்கலாம்னா, c greater than 1ங்கிறதுனால 3 into c minus 1 plus அங்க ஒரு 3 வரும், ஆல்ரெடி ஒரு 1 இருக்கு, plus 4ன்னு நான் இதை பிரிச்சிடலாம். 3c plus 1 எப்படி பிரிக்க போறேன், 3 into c minus 1 அங்க ஒரு 3 வரும், இங்க ஒரு 1 இருக்கு, plus okay. We have now come to this stage, that is e of k suffix 1 1 3c plus 1. இப்போ இதுல ரெண்டு sub cases வரலாம், c equal to 1 and c is greater than 1. c equal to 1 na this graph becomes nothing but k suffix 1 1 4. Keep in mind, okay, அது இருக்கட்டும். So suppose c வந்து greater than 1 na, now you can split this 3c plus 1 as 3 into c minus 1 plus 3 plus 1, that is 3 into c minus 1 plus 4 ன்னு நீங்க split பண்ணலாம். So அந்த splitting next இதுல பார்க்கலாம். See here, k suffix 1 1 3c plus 1 can be splitted into, இப்போ நம்ம பண்ண அதே டெக்னிக் தான். See here, இங்க 3 into c minus 1, இங்க 4 vertex place பண்ணிட்டு அதே ஸ்ட்ரக்சர் தான் இங்க வரும். இப்போ இதை நம்ம எப்படி ஸ்ப்ளிட் பண்ணலாம்னா, k suffix 3 into c minus 1 to 1 plus 1 2, 1 plus 1 2. சரியா, யூனியன் மீதி உள்ள கிராஃப் பாத்தீங்கன்னா இங்க 4 vertex, இங்க 1 vertex, இங்க 1 vertex, இது ஒரு கம்ப்ளீட் ட்ரைபார்டைட் கிராஃப். சோ k suffix 1 1 4. சரி, ஆல்ரெடி நம்ம வந்து c equal to 1 சொல்லும் போதும் k suffix 1 1 4 தான் வந்துச்சு. இப்போ இந்த கிராஃபை பாருங்க, இது வந்து ஒரு கம்ப்ளீட் பைபார்டைட் கிராஃப் வித் இங்க 3 into c minus 1 இருக்கு, இங்க 2 vertex இருக்கு, மல்டிப்ளை பண்ணீங்கன்னா mங்கிறது என்ன வரும், மல்டிபிள் ஆஃப் 3 வந்துரும். So this is p4 decomposable. அப்ப நீங்க எதை பத்தி மட்டும் பார்த்தா போதும், நான் இப்ப k suffix 1 1 4 p4 decomposable ஆனு மட்டும் பார்த்தா போதும். It is p4 decomposable. I have given a p4 decomposition for that. Okay, அப்போ நம்ம ஒரிஜினலா இருந்த பெரிய கிராஃப சப் கிராஃப்ஸா பிரிச்சு பில்டிங் பிளாக்ஸ், அதாவது இங்க நீங்க ரிவர்ஸ்ல போனீங்கன்னா தெரியும், பில்டிங் பிளாக் k 1 1 4ல இருந்து ஸ்டார்ட் ஆகி அதுக்கு மேல பில்டிங் கன்ஸ்ட்ரக்ட் பண்ணி லாஸ்டா எங்க போயிருது உங்களுக்கு, k suffix m1 m2 m3 க்கு போயிருது. சரியா, so this is the building blocks method. so ஒரு கேஸ் முடிச்சிட்டோம். so second case வந்துட்டோம், mi is congruent to 2 mod 3 for i equal to 1 2 3. so இதுவும் அதே மாதிரி தான், அங்க 3a plus 1 இருந்த இடத்துல plus 2 இருக்கு. so இதுல ரொம்ப சேஞ்ச் இல்ல, அதே மாதிரி தான். you can see here 3a plus 2 3b plus 2 3c plus 2. முத நான் இதை ரெண்டா பிரிப்பேன். see here 3a இங்க 2 னு பிரிக்கிறேன். அப்போ எனக்கு சப்கிராஃப் என்ன வரும், k suffix 3a 3b plus 2 plus 3c plus 2. இது முத சப்கிராஃபா வரும். யூனியன் ஒரு ட்ரைபார்டைட் கிராஃப் வரும், இங்க 2, இங்க 3b plus 2 3c plus 2 இப்படி வரும். சோ இத பாத்துட்டீங்கன்னா நம்பர் ஆஃப் எட்ஜஸ் m into n பாத்தீங்கன்னா இங்க 3 இருக்கிறனால மல்டிபிள் ஆஃப் 3 வந்துரும். சோ இட் இஸ் p4 decomposable. அப்ப இத மட்டும் பார்த்தா போதும். இதுல நான் எந்த பிரிப்பேனா, இப்போ 3b plus 2 ஸ்ப்ளிட் பண்ண போறேன். ஆல்ரெடி எனக்கு 3a முடிஞ்சிட்டு, அப்ப இங்க 2 மட்டும் தான் இருக்கும். see here, இங்க 2 இருக்கிறத நான் இங்க கொண்டு வந்துட்டு 3b plus 2 3b எங்க பிளேஸ் பண்ணிட்டு 2 இங்க பிளேஸ் பண்ணிருக்கேன். இப்போ அதே ஸ்ட்ரக்சர் தான் வரும், k suffix 3b this 2 plus 3c plus 2. so அது ஃபர்ஸ்ட் கிராஃபா வரும். அப்புறம் ஒரு கம்ப்ளீட் ட்ரைபார்டைட் கிராஃப் வரும் with 2 vertices here, 2 vertices here and 3c plus 2 vertices here. that is k suffix 2 2 3c plus 2. ஓகேயாப்பா, சரி. இப்போ பாத்துட்டீங்கன்னா இது வந்து அந்த ஒரிஜினல் தியரம் யூஸ் பண்ணீங்கன்னா நம்பர் ஆஃப் எட்ஜஸ் மல்டிபிள் ஆஃப் 3 வந்துரும். so it is p4 decomposable. so you have to care only about this one. so இப்போ இத வந்து p4 decomposable ஆன்னு பார்க்கணும். இதுக்கு அப்படியே நீங்க 3c plus 2 முன்னாடி போன இதில் into c minus 1 எல்லாம் போட்டோம், அதெல்லாம் வேண்டாம். 3c plus 2 மட்டும் நீங்க ரெண்டா பிரேக் பண்ணாலே you will get the answer. see here 3c இங்க 2 பிளேஸ் பண்ணிட்டீங்க. so அதே மாதிரி போட்டீங்கன்னா இது k suffix 3c இங்க 2 plus 2 4 யூனியன் ஒரு கம்ப்ளீட் ட்ரைபார்டைட் கிராஃப், ஒவ்வொன்றுலயும் 2 வெர்டெக்ஸ் இருக்கு, 2 2 2. இது தியரம் யூஸ் பண்ணீங்கன்னா it is p4 decomposable. இத மட்டும் நம்ம பார்க்கணும். இத நான் p4 decomposable உங்களுக்கு நான் கொடுத்திருக்கேன், decompositionே கொடுத்திருக்கேன். it is p4 decomposable. okay, this forms a decomposition. this forms another P4. அப்படி நான் உங்களுக்கு எல்லாமே கொடுத்துருக்கேன். It is P4 decomposable. So last case வந்துட்டோம். mi congruent to 0 mod 3 for at least 2i. இதை 2 சப் கேஸா ஸ்பிளிட் பண்ண போறோம். இது ரொம்ப சிம்பிள் தான். நம்ம வந்து வித்தவுட் லாஸ் ஆஃப் ஜெனராலிட்டி m1 m2 வந்து மல்டிபிள் ஆஃப் 3 எடுத்துக்கிறோம். ஸோ 3a 3b m3 வந்து 2 கேஸ். ஒன்னு m3 1 இருந்தா ஒரு கேஸ், நாட் ஈக்குவல் டு 1 ஒரு கேஸ். சரியா? ஸோ ஃபர்ஸ்ட் கேஸ்ல m3 நாட் ஈக்குவல் டு 1 எடுத்துக்கிறோம். ஸோ நான் இங்க போட்டிருக்கேன் 3a 3b. இங்க m3 என்னன்னு தெரியாது, m3னே போட்டிருக்கேன் நான். சரியா? ஸோ இதை எப்படி பிரிச்சிருக்கேன் அப்படின்னா, இதை வந்து தனியா பிரிச்சு எடுத்துட்டேன், மீதி இருக்கிறத தனியா எடுத்து எழுதிருக்கேன். இது என்ன உங்களுக்கு k suffix 3b, 3b, m3 இந்த வந்துருச்சு. k suffix 3b, m3. இது வந்து தியரம் யூஸ் பண்ணீங்கன்னா mn மல்டிபிள் ஆஃப் 3, அதனால this is P4 decomposable முடிஞ்சு போச்சு. சோ அப்ப இத பத்தி மட்டும் பார்க்கணும். what is this? This is k suffix 3a, இந்த ரெண்டை சேர்த்துறணும் 3b plus m3, 3b plus m3. இப்போ இத பார்த்துட்டீங்கனாலும் இதுவும் ஒரு கம்ப்ளீட் பைபார்டைட் கிராஃப். mn வந்து மல்டிபிள் ஆஃப் 3 வந்துரும், ஏன்னா இங்க 3a. So this is also P4 decomposable. இந்த கேஸ் உடனே முடிஞ்சு போச்சு. The complete tripartite graph is P4 decomposable. So last case என்ன எடுக்க போறோம்? m3 is equal to 1. இந்த ஒரு கேஸ் மட்டும் தான் left out. இந்த ஒரு கேஸ்ல என்ன பண்ண போறோம் அப்படின்னா 3a 3 into a minus 1, சரியா, பிளஸ் 3a தானே, பிளஸ் 3ன்னு பிரிக்க போறோம். சரியா? பிரிச்சு ப்ரீவியஸா உள்ள மாதிரி பண்ணோம் அப்படின்னா இது என்ன வந்துடும்? k suffix 3 into a minus 1, இந்த ரெண்டையும் சேர்க்க போறோம் 1 plus 3b யூனியன் ஒரு ட்ரைபார்டைட் கிராஃப் வரும் k suffix 3, 1, 3b. இந்த மாதிரி ஸ்ட்ரக்சர் வரும். இது நமக்கு தெரியும். kmn வந்து it is P4 decomposable since mn is multiple of 3 முடிஞ்சிடுச்சு. So the last one இதை மட்டும் நம்ம பார்த்தா போதும். k1, 3b, 3. இதுல 3b எப்படி பிரிக்க போறேன்னா 3 into b minus 1 plus 3ன்னு பிரிக்க போறேன். பிளஸ் 3ன்னு நான் பிரிக்கும் போது எனக்கு என்ன வந்துரும்னா இங்க k suffix 3b minus 1, இந்த ரெண்டையும் ஆட் பண்ணுவேன் 1 plus 3 4 யூனியன் ஒரு ட்ரைபார்டைட் கிராஃப் k suffix 1, 3, 3. நீங்க ஈஸியா செக் அவுட் பண்ணிடலாம். k suffix 1, 3, 3 வந்து P4 decomposable. நான் முன்னாடி decomposition கொடுத்தேன், அதே மாதிரி நீங்க செக் பண்ணிக்கோங்க. அண்ட் இது வந்து by theorem it is P4 decomposable. So overall the graph becomes P4 decomposable. எல்லா கேஸும் செக் பண்ணிட்டோம், எல்லா கேஸ்லயும் P4 decomposable வந்துருச்சு. So the complete tripartite graph is P4 decomposable. இதே மாதிரி you can prove that the complete R-partite graph with any arbitrary R is P4 decomposable if and only if the number of edges is multiple of 3 and the number of edges is greater than 3. So this is that is also proved. So we have come to the end of the session. Okay, so நான் வந்து proof techniques ஒரு 3 சொல்லியிருக்கேன் and 3 different types of decompositions நான் உங்களுக்கு கொடுத்திருக்கேன். So now come to the application. Startingலே சொன்னோம் experimental designs தவிர வேற எதுலலாம் applicationsனா group testings, மெடிக்கல் ஃபீல்டுக்குள்ள போயிடும், டிஎன்ஏ லைப்ரரி ஸ்கிரீனிங், ஷெடியூலிங் ப்ராப்ளம்ஸ், ஷேரிங் ஸ்கீம்ஸ், அப்புறம் சிங்க்ரோனஸ் ஆப்டிக்கல் நெட்வொர்க்ஸ். இந்த மாதிரி வந்து மெடிக்கல்ஸ் இதுல மெடிக்கல் ஃபீல்ட்ல நிறைய அப்ளிகேஷன்ஸ் நமக்கு இருக்கு. இன்னும் நிறைய அப்ளிகேஷன்ஸ் இருக்கு. Now it is your term to find them out. Good luck to all of you. Thank you everyone for your patience. And so dear students, be aware that நீங்க ரிசர்ச் வந்து வேண்டாம், நான் பிஜி முடிச்ச உடனே வந்து நான் வந்து ஜாபுக்கு போயிடுவேன் அப்படி யோசிக்காதீங்க. ஃபார் டைம் பீயிங் எனக்கு ஃபேமிலி சிச்சுவேஷன், நான் உடனே ஜாப் போகணும் அப்படின்னு நினைச்சா கூட பிஜி முடிச்ச உடனே நீங்க ரிசர்ச்ல ஜாயின் பண்ணீங்கன்னா மினிமம் ஸ்டைஃபண்ட் வந்து உங்களுக்கு கவர்மெண்ட் எவ்வளவு ப்ரொவைட் பண்ணுவாங்கன்னா ஸ்டார்டிங் ஃப்ரம் 25,000. ஸோ நீங்க ஒரு ஜாப் போனா கூட அவ்வளோ அமௌண்ட் உங்களுக்கு கைக்கு வருமானு தெரியாது. ஸோ அதர் மேஜர் ஸ்டூடெண்ட்ஸ்க்கு கூட நீங்க வந்து ப்ராக்டிகலுக்கு அவங்க ஸ்பெண்ட் பண்ண வேண்டியது வரும். பட் நம்ம டிபார்ட்மெண்ட்டை பொறுத்தவரையில நீங்க பிரெயினுக்கு மட்டும்தான் ஒர்க் கொடுக்க போறீங்களே தவிர மற்றபடி அந்த அமௌண்ட் கம்ப்ளீட்டா நமக்கு சேவிங்ஸ் தான். சப்போஸ் ஹாஸ்டல்ல ஸ்டே பண்ணா அதுக்கான அமௌண்ட் ரிமைனிங் எல்லாமே நமக்கு சேவிங்ஸ். ஸோ பிஜி ஸ்டூடெண்ட்ஸ் தாராளமா நீங்க ரிசர்ச்குள்ள போகலாம். ஸோ இது வந்து ஒரு நல்ல ஸ்டார்ட்டா இருக்கும். நிறைய ஓப்பன் ப்ராப்ளம்ஸ் இருக்கு, இன்ஃபைனைட் நம்பர் ஆஃப் ஓப்பன் ப்ராப்ளம்ஸ் இதுல இருக்கு. நீங்க ஏதாவது ஒன்னு எடுத்து அட்டெண்ட் பண்ணா உங்க தீசிஸ் நீங்க கம்ப்ளீட் பண்ணிடுவீங்க. அப்ப யூஜி ஸ்டூடெண்ட்ஸ் நினைக்கலாம், மேம் அப்ப நாங்க என்ன செய்யன்னு பார்த்தா இப்ப யூஜிசியே வந்து அனௌன்ஸ் பண்ணிருக்காங்க, பிஜி இஸ் நாட் நெசசரி ஃபார் டூயிங் ரிசர்ச். யூஜி இருந்தாலே போதும்னு சொல்லியிருக்காங்க. இன்னும் அதுக்கு ரூல் இம்ப்ளிமெண்ட் பண்ணாங்களான்னு தெரியல. பட் தே ஹவ் ஸ்டார்டட் டு திங்க் அபவுட் தட். So UG complete பண்ணா கூட you can enter into research and you can get a stipend of about from starting 25,000 உங்களுக்கு வாங்கலாம். சரியா? So நீங்க படிக்கும் போதே you concentrate in research also. Side by side ஒரு ப்ராப்ளம் எடுத்து நீங்களா ஒர்க் பண்ணுங்க, கொஞ்சம் டைம் ஸ்பெண்ட் பண்ணி அதை படிங்க. சரியா? So it will be useful to you. So these are all the references. ஸோ டீகம்போஷன் ஆஃப் கிராஃப்ஸ்ல ஒரே ஒரு புக் தான் இருக்கு, ஜுராஜ் போசாக்ங்கிற புக். இதுல தான் எல்லாம் என்னெல்லாம் ஃபைண்ட் அவுட் பண்ணியிருப்பாங்களோ, அண்ட் வெரி ஓல்டு புக், 1990ல பப்ளிஷ் ஆனது தான் இருக்கு. அண்ட் அதை தவிர டிசைன்ஸ் நிறைய இருக்குமே தவிர டீகம்போஷனுக்கு வேற புக் கிடையாது. யூ ஹேவ் டு ரீட் த பேப்பர்ஸ். அண்ட் நவ் இஃப் யூ ஹேவ் எனி டவுட்ஸ் யூ கேன் ஆஸ்க் டு மீ. தேங்க்யூ எவ்ரி ஒன்.
That was extremely informative. It will be definitely useful for us in solving similar problems later. Thank you, ma'am, for devoting your precious time with us.
Thank you, ma'am.
Yeah, girls, you'll be having 10 minutes. So I request my dear friends to assemble here sharply. Thank you. Thank you, ma'am.
Thank you, ma'am. Thank you.
Thank you, ma'am. Girls, everyone must assemble here sharply after 5 minutes.
Good morning, ma'am.
குட் மார்னிங் மேம்.
Good
நல்லா
morning,
இருக்கீங்களா
ma'am.
மேம்?
நல்லா இருக்கேன் மேம். நல்லா இருந்துச்சு மேம், உங்க டாக் சூப்பரா இருந்துச்சு மேம்.
தேங்க்யூ மேம். தேங்க்யூ மேம்.
நல்லா
நீங்களும்
நல்ல இன்டெப்த் கான்செப்டா இருந்துச்சு மேம்.
அது
டீகம்போசிஷன்ல.
ஓகே மேம். அது கொஞ்சம் ஸ்டார்ட் பண்றதுக்கு பிள்ளைங்களுக்கு கொஞ்சம் நல்லா இருக்கும்னு சொல்லிட்டு தான் அதை எடுத்தேன் மேம்.
கண்டிப்பா கண்டிப்பா நல்லா இருந்துச்சு மேம். தேங்க்யூ மேம்.
தேங்க்யூ.
என்னோட வாய்ஸ் ஆடிபிளா இருக்குல்ல மேம்?
கிளியரா இருக்கு மேம். கிளியரா இருக்கு.
தேங்க்யூ ஸோ மச் மேம். தேங்க்யூ.
நீங்களும் உங்களுக்கும் கிராஃப் தியரி தானா மேம் ஏரியா?
எஸ் மேம், எஸ் மேம். கெமிக்கல் கிராஃப் தியரி மேம் என்னோட ஏரியா
கெமிக்கல்.
வந்து.
ஓகே. அப்ளிகேஷன் ஓரியன்டடா.
அப்ளிகேஷன் ஓரியன்டடா இருக்கும்.
ஓ
பட்
சரிங்க மேம்.
கான்செப்ட்ஸ் ஃபுல்லாவே மேத்தமேட்டிக்கல் பிளஸ் அப்ளிகேஷன் ஓரியன்டடா கம்ப்ளீட்டா இருக்கும் மேம்.
ஓ சரிங்க மேம். சரி. நைஸ் மீட்டிங் யூ மேம்.
தேங்க்யூ ஸோ
ஃபர்தரா
மச்
நம்ம
மேம்.
மீட்
தேங்க்யூ.
பண்ணலாம் மேம்.
கண்டிப்பா கண்டிப்பா மீட் பண்ணலாம் மேம்.
ஓகே மேம்.
உங்க கான்செப்ட்ஸ்லாம் ரொம்ப பிடிச்சிருச்சு. நல்லா இன்டெப்தா இருந்துச்சு. நல்லா இருந்துச்சு மேம்.
சரிங்க மேம். சரிங்க மேம். தேங்க்யூ மேம்.
தேங்க்யூ.
ஓகே மேம். ஓகே மேம்.
Shall we start, ma'am? Yes.
Yes, ma'am. Yes, ma'am. Is it audible, ma'am? Am I
Yes.
audible?
Yes, ma'am. Yes, ma'am. Audible.
Okay, ma'am. Thank you, ma'am.
Having a variety of speakers can liven up a webinar and drive real engagement with the audience. Now I request Mrs. Abina Razale, Assistant Professor, Department of Mathematics, SF, Holy Cross College, Nagarkot, to extend a hearty welcome to our next resource person.
A very good morning to one and all present here.
Morning to A very good morning to one and all present here. It's an immense pleasure for us to introduce our resource person, Dr. Rishwana, an Assistant Professor of Mathematics in VHN Sendi Kumara Nadar College, Autonomous Vizinagar. She completed her PhD in the year 2019 under the topic A Study on Topological Indices from Yamos University. She also passed set exam in 2016. She was a gold medalist during her MPhil. Her research interest is on graph theory and the area of specification is chemical graph theory. She has teaching experience for almost 11 years. She has also worked as assistant professor of mathematics in National College of Engineering, Tirunelveli. She also worked as head and assistant professor of mathematics in Sadakatula Appa College, Tirunelveli. She published 14 articles in international and national journals. She also presented 17 articles in international and national level conferences. She attended many national and state level seminars and conferences. She acted as a resource person and delivered many lectures. She received Certificate of Excellence in Reviewing from Asian Journals of Mathematics, Journals of Advances in Mathematics and Computer Science, and also in Journal of Scientific Research and Reports. It's an honor and privilege for us to have a webinar section. On behalf of the staff and students, we extend a warm welcome to you, ma'am.
Thank you, ma'am.
It's an honor and it's a great honor to have you today with us. Once again, I welcome you, ma'am. Thank you.
Thank you, ma'am.
Graph theory might sound abstract topic to you, but it's not. There are actually a number of useful and important applications of graph theory. Here comes our honorable resource person, Dr. E. Rizwana, Assistant Professor of Mathematics, VHN Sendikumar Nadar College, Virudhunagar, to discuss about the real-life applications in graph theory. I welcome you, ma'am.
Thank you, ma'am. Good morning. Am I audible, students?
Yes, ma'am, it's audible.
Okay, ma'am. Hi, students. Good morning, everybody. Good morning, one and all present here. It gives me immense pleasure to speak among you in the state level webinar of graph decomposition and on graph applications. First of all, I would like to thank the secretary, principal, and the HOD ma'am, Kavita ma'am, for giving me this great opportunity to speak among you about the real life applications of graph theory. I am very appreciating the organizers for conducting such a beautiful seminar, and my thanks goes to Mary Janita for introducing me to the HOD. I thank one and all for giving me this great opportunity. Students, are you there? Can you hear me?
Yes, ma'am.
Even though this is a mode of a presentation through online, a seminar through online, I like to have some interaction with the students. So I think the interaction with the students will create this seminar a great success. So students, please have a note. I'm going to ask some questions. I'm going to give some of the interesting concepts in graph theory to you. So please be ready to cherish the applications in real life. Now let me share the screen now. Is the screen visible, ma'am?
Yes, ma'am. Yes, ma'am.
Yes, the topic I have chosen is real-life applications of graph theory. So graph theory is a very interesting and wide area in mathematics, which has a great number of applications to all the subjects, including physics, chemistry, biology, medical sciences, computer science, pharmaceutical science. In many areas, it has a wide range of applications in graph theory. So graph theory has become a very interesting part in the research area in mathematics. So most of the researchers choose graph theory because it has variety of applications in varied of subjects. So to start with, I'll just give a small definition of a graph. A graph is nothing but a collection of dots, and dots are called as the vertices, and the lines between the dots are called as the edges. So wherever you have the concept of dot and edges, you call it as a graph. Graph theory is a study of graphs, which are mathematical structures used to model the pairwise relationship between the objects. Whenever there is a pairwise relationship, we can use graph theory. So here I have depicted some of the example, small graph, a simple graph and a multi-graph. Here, a simple graph is a graph without loops and multiple edges. A graph with loops and multiple edges is called as a multi-graph. See here, in this graph, there are no loops. But here in this graph, there is a loop which starts from the particular vertex C and ends at the same vertex C. So multiple edges is the edge which is formed between the two vertices. So already there is a edge between A and B, and there is one more edge between A and B, and this forms the multiple edges. A graph without multiple edges is called as a simple graph, and a graph with loops and multiple edges is called as a multi-graph. So directly I want to enter into the topic of graph models. So I'm going to depict you some of the examples where graphs can be used. See, if you are having some cities and the flight connection between the cities, you can model a graph. See, the cities can be considered to be the vertex, and the flights running between the cities can be considered to be the edges. Similarly, if you are having some people and pair of friends between those people, you can construct a graph, and that graph is called as a friendship graph. So see, the vertex is considered to be the people, and the relationship of friendship can be taken as the edges. Similarly, authors can be considered as the vertices, and co-authorship between the authors can be considered as edges. Telephones in the office can be considered to be the vertex, and telephone calls between the telephones can be taken to be the edges. Similarly, in computer science, in internets, web pages can be considered to be the vertices, and the linkings can be taken to be the edges. In medical field, genes can be taken to be the vertices, and their regulatory aspects can be taken to the edges. In such a way, we can model a graph. See here, I have depicted here internet routing graph. Wherever the internet routing is there, I have depicted a graph over here. Anything can be converted to a graph model and can be studied easily. So I'm going to present you some of the varying applications of graphs. So graphs are used in computer networks, medical analysis, to solving the shortest path problem between cities, scheduling the exams, and assigns channel to the television stations. It is also used in sports scheduling, mobile towering, traffic signals, etc. So in the upcoming speak, I'm going to present you some of the areas where graph can be depicted easily and some of the varying applications, and I'm going to express you some of the different problems you can use graph theory. So first, a network topology. See an electrical circuit. You might have come across the electrical circuit with the resistors, capacitors, etc. So network topology is a graphical representation of electrical circuits. It is useful for analyzing the complex electric circuits by converting them into network graph. See the visualized example over here. This is an electrical circuit. This electrical circuit contains 4 important components A, B, C, and D. This is depicted into a directed graph. A directed graph is a graph in which the direction is mentioned. See here in the part 3, the direction is mentioned. In part 5, the direction is mentioned. So even an electrical circuit can be converted to graph theory. So here I have given you an example of a tripartite network in medicine. You must have come across a bipartite network. Bipartite network consists of 2 vertices, 2 vertex sets. But in tripartite network, it contains 3 set of vertices. So I am going to separate the 3 set of vertices to be first one as the abdominal pain, and that is considered to be a single vertex set. And the remaining symptoms are considered to be the second vertex set, and the persons affected with these symptoms are considered to be the third vertex set. See, the vertex sets are split into 3 sets. One is the abdominal pain, next one is the supporting symptoms, and next to the persons affected with these symptoms. So these abdominal pain together with the diarrhea, appendicitis, Barrett esophagus, etc. And the persons who are get affected as shown in this tripartite network in medicine. So a graph can be also used in medicine. So actually the cancerous cells which they have detected today are nothing but a multipartite graph. So a tripartite graph is a set in which the vertex set is split into 3 sets. What do you mean by multipartite graph? Means a graph in which the vertex set is split into a n number of vertices. So this n number of networks forms the main graph in the cancerous cell. So if you see through the telescope, we can see the tissues affected by cancerous, and you can convert the tissues affected by a cancerous into a graph cell, and studies are going on nowadays. It is really an interesting application of graph theory even to the field of medicine, that is in the treatment of cancer. So see a disease contact graph. If you see through the microscope, a disease contact graph will be in such a way. So see, this one looks like a multipartite graph. It has some 3 colors, more than 3 colors. Colors with green, yellow, red, together with the edges. This multipartite graph are used to study the properties of some of the cancerous cells. So they'll understand where the concentration is more, and they'll study the cells which are getting more defected. So next is an interesting next area where the graph theory is applied is the mathematical chemistry and the chemical graph theory, and this is my area of research. So mathematical chemistry is engaged in the novel applications of mathematics to chemistry. Chemical graph theory is a branch of mathematical chemistry which applies graph theory to study their molecular structure. See, I have depicted you an example of a chemical structure. See, it is an 5-isobutyl, 3-isopropyl, 2, 3, 7, 7, A pentamethylonine. This is the structure of this chemical compound. I have converted this chemical compound to a graphical structure. See the graphical structure. I have converted this chemical compound to a graphical structure. These vertices are nothing but the carbon atoms, and the bonds are considered to be the edges. See, I have given you another example. A molecular graph or chemical graph is a representation of the structural formula of a chemical compound in terms of graph theory. You must have come across many molecules in chemistry. So even in school, you must have studied about ethane, propane, butane, pentane, etc. These molecules, they grow in the structure with their carbon atoms. Ethane has 2 carbon atoms. Propane has 3 carbon atoms. Butane has 4 carbon atoms, pentane has 5 carbon atoms, etc. So I am going to convert this structure to graph theoretical structure. See, this carbon is choose to be the vertices, and the bond between the carbon is choose to be an edge. So this depicts a graph P2, the path graph P2. Similarly, the propane molecule depicts a path graph P3. So here we can convert the chemistry molecule compounds in chemistry to the path graph. So vertices corresponds to the atoms, that is carbon atoms, and the edges corresponds to the bonds between them. After converting a particular molecule to a graph, we can apply some of the formulas, we can apply some of the concepts in graph theory to study the properties of those molecules. See, I have given you an example. This is nothing but harmonic index H of G, which is nothing but sum of the value 2 by degree of U plus degree of V. So here there is only one H and there are two vertices U and V. I'm just going to add the degree and I'm going to take the summation. So this will give you a number, and that number is called as a topological index of this particular graph P2. Similarly, for P3 also, we can calculate the harmonic index using this formula, and using this formula you will get a particular number which depicts the properties of this graph P3, and this property can be applied again to the chemistry to understand the physical and chemical properties. In this way, graph theory can be applied to variety of subjects. Here, this is in chemical graph theory. My area of research is chemical graph theory, and I have introduced the concept of non-neighbor indices in this chemical graph theory. So, see some of the interesting equivalent terms in the chemical and mathematical term. So, in chemistry, atom is matched to a vertex, molecule is matched to a molecular graph, covalent bond is matched to a edge, a cyclic hydrocarbon, that is a hydrocarbon without cycles, are matched to a tree. Alternate structure in chemistry is matched to a bipartite graph in a graph theory. Valency of an atom is matched to the vertex degree. Skeletal structure is matched to the hydrogen depleted graph. So topological matrix is adjacent to the adjacency matrix. You must have understand the concept of adjacency matrix. Once a graph is depicted, you can draw the particular matrix for those graphs. And using that matrix, you can compute the eigenvalues, etc. And in this way, you can compare many of the chemical terms with the mathematical terms in graph theory. So completely, a graph theory can be applied to the chemistry to understand the physical and chemical properties of components. So now I'm going to start with some of the problems and the real life problems applied through graph theory. So first you have to understand the concept of weighted graph. A weighted graph is nothing but a graph which contains a weight. So graph with edges, it must contain vertices, it must contain edges together with some real number, positive real number called as the weight. See here, between the vertex 1 and 0 and 1, the weight is 3. Between the vertex 1 and 7, the weight is 4. So in this way, we can depict a graph. So friendship graph can be depicted by using these weight. Intensity of friendship can be measured between these people. So suppose there are 8 members, you can draw the 8 members, and the relationship between the members can be depicted using this intensity. So this 4, 3 can be considered as intensity. If this is a communication graph, suppose if I'm depicting this as a communication graph, this weight can represent the cost or maintenance cost or traveling cost or distance, etc. So a weighted graph is a graph together with the weight on the edges. So with this concept, I'm going to present you the how to find out the shortest path between the two vertices. Students, can you see a graph over here? Just now, you are going to find out the shortest path between U0 and V0. The shortest path problem is finding a path between the two vertices in such a way that sum of the weights of its constituent edges is minimized. So I'm giving you a work here, an interesting work. Please find the shortest path between U0 and V0. Students, are you there? You can find the shortest path between U0 and V0. The main purpose is that the cost between U0 and V0 must be minimized. Have a look over on this graph. Look into this graph. If anyone has an answer, you can please convey it to me. The shortest distance between U0 and V0. You are going to find out the shortest path between U0 and V0. So I think students are seeing. So in the next image, I'll show you an example. So here I have depicted an shortest path between U0 to V0. See, here there is a path between U0 to V0. So see the distance, how it moves. From U0 to this vertex, the distance is 1. The minimum cost is 1. From this vertex to this vertex, the cost is 9. From this particular vertex to this vertex, the cost is 1. Similarly, from this vertex to the last vertex V0, the cost is 4. So the total cost of this path is 14. The question is that, can you find another path with a minimum cost? So here the cost between U0 and V0 is 14. So because 9 plus 1 plus 1 plus 1 plus 2 is 14. And the question is that, can we find a path which is minimum to that of 14? So in the next graph, I have depicted you here another interesting path between U0 and V0. See the path over here. So between U0 to this vertex, the distance is 2. From this vertex to this particular vertex, the distance is 1. From this vertex to the down vertex, the cost is 3. From this vertex to this vertex, the cost is 1. And from this vertex to this vertex, the cost is 2. And similarly, from this vertex to this vertex, the cost is 1. And from this to this, the cost is 1. And finally, to reach V0, the cost is 2. Even though this seems to be a longest distance, but the cost seems to be minimum. See, when you add up the quantities, 2 plus 1 plus 3 plus 1 plus 2 plus 1 plus 1 plus 2, you get the answer as 13. While the previous path seems to be a simplest path, but the cost remains to be 14. But here the path seems to be the longest path, but the cost seems to be 13. So in order to move from the particular point U0 to V0, I have to choose this path in order to minimize the cost. So this can be applied in terms of, instead of U0 and V0, you can fix some 2 cities and you can find out the path between 2 cities in order to minimize the cost of transportation. And this is an interesting example of a weighted graph in the real life situation. And next is the Dijkstra's algorithm, very interesting algorithm. In this algorithm, you alone can't find out the distance between the 2 vertices, but you can also find out the distance between a particular vertex to the remaining vertices. So see here, the algorithm was discovered by the Dijkstra's in the year 1959. It finds not only the shortest U0 V0 path, but also the shortest path from U0 to remaining all the other vertices of G. See, I have depicted a graph over here. See the particular vertex U0 in the middle. This vertex is U0. I am going to fix this vertex and I'm going to fix this vertex. I'm going to find out the distance from this vertex to the remaining 7 vertices over here. I am going to apply an algorithm to find this. So I'm going to fix a particular vertex U0 and I'm going to find out the shortest distance between not only a particular vertex, but all the remaining 7 vertices. See, I have given you an example here. First, I'm going to choose the very smallest path. See, between U0, from U0, there are 5. The degree of U0 is 5. So from U0, that starts 5 edges. 1. Here one starts with 2. Here it starts with 7. Here it starts with 4. Here it starts with 8. So I'm going to choose the minimum path to be A. So the distance between U0 to A is 1. After fixing this, I am going to find out the distance between u0 to some other vertex. See, from u0, next I can choose this particular vertex 2. So it is depicted in the green color. So distance between u0 to b is 2. So first I have choose the vertex A. The distance between u0 and A is 1. Second, I have chosen a vertex B. The distance between the vertex u0 and B is 2. So the distance is slightly increasing. So next to C, the vertex C comes. So I am going to travel from u0 to this vertex with the distance 2. Then again from this vertex to the particular vertex C with distance 1. So totally distance between u0 and the vertex C is 3. So I have fixed the vertex A, I have fixed the vertex B, I have fixed the vertex C. Similarly, I want to fix the next vertex D. If I choose some other vertices, the distance becomes more. So if I am choosing here, the distance will be 3. If I am choosing this vertex, the distance will become 9, etc. So I am going to choose the vertex D. So see, the distance between u0 and D is 4. So in this way, I am going to apply the algorithm from the vertex u0. I am going to choose a particular vertex which has the shortest distance. So I have selected my A, I have completed my B, I have completed my C, and here comes my vertex D. In next step, I'm going to find out the distance between the vertex E, u0 and E. See, from u0 and E, the distance is 2 plus 1 plus 3, the distance is 6. Similarly, the distance between the vertex u0 and F is 6. See the path I have chosen. From u0, I move through this vertex as 4. And then again, I come to this vertex with a distance of 2. So totally, the distance is 6. Next, finally, I choose the vertex G, which has a distance of 9. See the way I have chosen. From u0 to this vertex, the distance is 2. From this vertex to here, you get the distance as 1. And finally, you get the distance as 6. 6 plus 1 plus 2, the distance is 9. So finally, I have computed all the distances from the particular vertex u0. See, from this particular vertex u0, I have found out the distance between A. I have found out the distance between B. I have found out the distance between C. I have found out the distance between D. Then I have depicted my E and F and G. So totally, this algorithm is called as the Dijkstra's algorithm, and this algorithm is used to find out the shortest distance between some u0 to the remaining vertices. See, if I remove all the remaining vertices and if I just draw the distance between these vertices, I get the tree. See, this image is the image of a tree. So between u0 to A, the distance is 1. From u0 to B, the distance is 2. From u0 to C, the distance is 3. Similarly, from u0 to 4, the distance is 4, 6, 6, and 9, etc. At each stage, the shortest path together form a connected graph without cycles. Such a graph is called as a tree, and this algorithm provides a tree growing procedure. At each stage, if you see, a tree develops from u0. And this algorithm is called as a Dijkstra's algorithm. So this algorithm can be used to find out the distance between our home. Consider this vertex u0 as our home, and the distance between this A, B, C, D, E, F, G can be considered as some places. And you can find out the shortest distance between your home and some of the places. So next, here is an example of a Dijkstra's algorithm, and this algorithm can be applied in C++ programming or Python programming languages, and shortest path can be obtained in various graphs easily. Even for a graph with a large n, you can apply this Dijkstra's algorithm through computer programming to find out the shortest path. And this is the first real-life application of this weighted graph using the shortest path algorithm. Next, I would like to show you some of the interesting property of Sperner's lemma and Brouwer's fixed point theory. So here, see here, there is a triangle. There is a big triangle. Simplical subdivision. I'm going to subdivide this triangle into small triangles. See, I have divided this big triangle into small triangles. About 12 triangles I have divided this picture. I am going to give a labeling to this triangle. So for each of the meeting points, I am going to label. I am going to label by using 0, 0, 2, 2, 1. Only I am going to use the three labels 0, 1 and 2, etc. This is called as proper labeling. If the sides get exactly two numbers, see, the left side gets exactly two numbers 0 and 2. The right side of the triangle gets exactly two numbers 0 and 1. And the base triangle gets exactly two number 1 and 2. And this is called as proper labeling. So I have taken a triangle. I have subdivided the triangle, and this is called as simplical subdivision. After subdividing the triangle, I am giving proper labeling. Labeling means giving a name to the vertices. I am going to label using 0, 1 and 2, etc. See now, this triangle, again I'm going to give some names to the particular faces. So for particular first triangle, I'm giving the name as T1. For the next triangle, I'm going to give the name as T2, T3, T4, etc. up to T12 triangles. And the area which is outside the triangle is named as T0. See, I'm going to name that each sub-triangles by using T1, T2, etc. up to T12. The area outside this triangle is named as T0. So the Sperner's lemma explains that every properly labeled simplical subdivision of a triangle has odd number of distinguished triangles. So you have to understand the concept of what is distinguished triangle. A triangle which gets the points 0 and 1 and 2. A triangle which gets the label 0, 1 and 2 is called as the distinguished triangle. See, I have given you with the green color here. 0, 1, 2 is a triangle with green color. This is a distinguished triangle. Similarly, T12 is a distinguished triangle with a 0, 1, 2 labeling. Similarly, T9 is a distinguished triangle with the labeling 0, 1 and 2. So, here, the number of distinguished triangles are always odd. That is, there are 3 distinguished triangles in this figure. This figure can be depicted to a graph theoretical model. See here, for each face, each triangle T1, I am placing a vertex V1, V2, V3, V4, V5, etc. up to V12. See, for a particular T1, I have placed V1. For T2, I have placed V2. For T3, I have placed V3. For T11, I have placed V11, etc. And for T0, I have placed a vertex V0. Now I am going to mark the edges in such a way that I will mark an edge if there exists a particular side between these two triangles. See, between T0 and T2, there is a side. So I am going to join it with an edge. Similarly, see, between T3 and 3, 4, there is a particular side which is common to both T3 and T4. So I am going to join with an edge. Similarly, there is a common side between T4 and T5. So I am going to join V4 and V5. Similarly, between V3 and V4, I have a common side. So I join the vertices. Similarly, I join V12 with V8. So T12 and T8 has a common side. So I join that one. T8 and T9 has a common side. I join with the edge. So I converted this simplical subdivision of a triangle into a graphical structure. Just please view on this graph. Just please view on this graph. You can see only 3 vertices with a degree 1. Just see, just view this graph. It is a really an interesting property or interesting application of the simplical subdivision. You can just see 3 vertices. See, the vertex V2 has degree 1, vertex V12 has degree 1, vertex V9 has degree 1. So totally only 3 vertices has degree 1. See, correspondingly, there is only 3 triangles with a distinguished triangle. See, T2, T12, T9s are distinguished triangles. See how a simplical algorithm can be applied to graph theory to find out the distinguished triangle. See, every properly labeled simplical subdivision of a graph has odd number of distinguished triangles. This odd number says that there are only 3 vertices of degree 1. The vertex with degree 1 can be considered to be a distinguished triangle. So if you are having a very large picture of a simplical subdivision of a triangle, you can apply the same algorithm to find out the distinguished triangles. You can find out the distinguished triangle, and this property of Sperner's lemma is applied to find out the Brouwer's fixed point theorem in real analysis. See, even graph theory is applied to real analysis. The theorem is that every continuous mapping f of a closed n disk to itself has a fixed point. This Brouwer's fixed point theorem is an immediate consequence of this Sperner's lemma, which was found in the year 1928. This Brouwer's fixed point theorem has a wide range of applications in modern mathematics. So we have seen a second example where the graph theory is applied to the real analysis. Next comes the concept of spanning tree. See, the concept of spanning tree is that from the biggest graph, I am going to take a small graph T. See, a spanning tree is a subgraph of a undirected connected graph which includes all the vertices of a graph with the minimum possible number of edges. See, this is a K5 graph. That is a complete graph with the 5 vertices. You must have come across the complete graph with 5 vertices. For this complete graph, I have drawn a spanning tree. See, in spanning tree, all the 5 vertices will be available, and you have to draw as minimum number of edges as possible so as to get a connected graph. See here, I have taken all the 5 vertices. I have chosen minimum number of edges. I have just chosen only 4 edges, and this depicts a spanning tree. So this is the graph K5, and this is the spanning tree of this graph K5 with minimum possible number of edges. See, the minimum edges is just 4 edges I have chosen, and this is an spanning tree. This spanning tree becomes an optimal tree if we give a weight to this graph. The minimum weight spanning tree of a weighted graph is called as an optimal tree. So yeah, you must have understand the concept of spanning tree in graph theory. So optimal tree is a concept where we apply a weights to this graph K5. So I'm going to show you one of the application of this optimal tree or spanning tree. See the connector problem. See, I have given you a table. This table is nothing but it gives the distance between the 2 cities in America. See, say London, Mexico City, New York City, Paris City, Peking City, and Tokyo. I have taken some of the 6 cities, important cities in America, and I have given the distance between flight distance between these cities. So L represents London, MC represents Mexico City, New York City, Paris, Peking, Tokyo, etc. I am going to construct a network connecting these cities with the minimum distance. So this depicts the distance, and I'm going to construct a network connecting these cities with the minimum distance. See, this table, I am converting it to a graph. See, there are 6 vertices, L, MC, NY, PA, PET. With the 6 vertices, I have depicted a graph. This graph is the K6 complete graph on 6 vertices. I have mentioned all the distance between each and every cities in the hundreds of kilometers. So if it is 5, 5, 5, 8, I have just depicted as 56. If it is 3, 4, 6, 9, etc., I have depicted with 35, etc. So I have converted a problem with the distances to a graph theoretical concept of complete graph K6. Now I am going to find out the shortest distance between these cities. I am going to apply the concept of optimal tree concept. See here, as the distance between L and PA, that is London and Paris. Look at the figure over here. The distance between London and Paris is very minimum. It has a distance of 2000 miles. So just I'm going to pick out this edge as my first edge. See that between L and PA, that is between London and Paris, I'm going to choose the first edge with the distance of 2. Next, I'm going to choose the distance edge between T and PE. So it is with a 13. Tokyo and Peking. Next, I'm going to choose an edge between MC, Mexico City and New York with a distance of 21. So first I have chosen L to PA with a distance 2, next to Tokyo to Peking with a distance of 13, and with for Mexico City to New York with a distance of 21. So I have chosen already 3 edges. I have to connect the cities London, New York. I have to connect the cities with London and Peking. There is no connection between London and New York and London and Peking. So I am going to choose another edge 35 between London and New York. See, here I am going to choose an edge between London and New York. Finally, I am choosing an edge between London and Peking. In this way, if I am choosing, I am getting a final tree which is called as an optimal tree. First, I chose this one with the 2. Next, I chose with the 13 distance. Next, I chose this edge with the 21 distance. Next, I chose an edge between London and New York with the 35 distance. And next, I chose a distance between London and Peking with the 51 distance. So finally, I got an optimal true. And this is nothing but a spanning tree. This is nothing but a spanning tree of the graph K6. See, a graph K6 is converted to a spanning tree, and this can be applied to find out the distance between cities. And this problem is called as the connector problem. And this algorithm for solving the connector problem is Kruskal's algorithm. I have given you the algorithm. This algorithm can be converted similarly using programming using C++ and Python to find out the distance between many other cities also. So this is the third application where we have applied the concept of spanning tree and the optimal tree to find out the distance between various places. Next comes the concept of vertex connectivity. See, vertex connectivity is an interesting concept in graph theory. The smallest number of vertices whose deletion causes a connected graph to get disconnected is called as a vertex connectivity. See here, there are many vertices here. If you just delete a particular vertex, the graph should get disconnected. See here, this is the graph G with the 5 vertices. I have removed the middle vertex. When I remove the middle vertex, the graph becomes a disconnected graph. It is a totally disconnected graph because all the vertices gets isolated. See here, this is the graph, another graph G. I have disconnected these 2 edges. See, I have disconnected these 2 edges. And if I disconnect these 2 edges, the graph becomes disconnected. So the connectivity is nothing but number of vertices required to disconnect the graph. In this graph, the connectivity is 1. In this graph, the connectivity is 2. So next, let us see the concept of edge connectivity. Just like vertex connectivity, edge connectivity is also, the edge connectivity also called as line connectivity of a graph is the minimum number of edges whose deletion from a graph will disconnect the graph. See, here is the same graph with the 5 vertices. If I delete this particular edge, the graph gets disconnected. See, if I delete this particular edge here, the graph gets disconnected. So here is an example of another graph G with the 5 vertices. If I delete these 2 edges, this one and this one, the graph gets disconnected. So K dash of D is nothing but the edge connectivity number. Here 1 edge is enough to make the graph disconnected. Similarly, here 2 edges is needed to make the graph disconnected. This is an interesting concept in graph theory. This vertex connectivity and edge connectivity is used to construct a reliable communication network. See, suppose a graph represents a communication network, the connectivity or the edge connectivity becomes the smallest number of communication stations whose breakdown would jeopardize the communication in the entire system. This means that suppose you are having a computer network. Suppose a hacker wants to disturb this communication network. If he knows the concept of edge connectivity or the vertex connectivity, he can directly go and demolish that particular system so that the total network gets collapsed. So, if you are making a link higher the connectivity, the edge connectivity, the more reliable is a network. So in this example, consider this network to be a computer network. Suppose the hacker damages this computer, the total network gets collapsed. So similarly in here, if a hacker disturbs this particular vertex and this particular vertex, the total network becomes collapsed. So if the connection is more, the system is said to be more reliable. So a complete graph is said to be more reliable because complete graph is interlinked with all the vertices. So when we interlink all the computers using the concept of a complete graph, it is very difficult for the hackers to demolish the system. So this is a very good, beautiful application of the connectivity in concession of the reliable network. So higher the connectivity, the edge and the edge connectivity, the more reliable is the network. When the connectivity number is more, it is very difficult for the hackers to jeopardize the communication in the system. So next comes the interesting problem called as the Königsberg's bridge problem. This problem is considered to be the father or main problem in graph theory. So see here, there are 7 bridges. Can you see? There are 7 bridges. 1, 2, 3, 4, 5, 6, 7. And intermediately here, there's one bridge. The girl who is standing here is an area of land and it is depicted to be A. And the land over here is depicted to be B. Land over here is depicted as C, and land in between these two bridges are depicted as D. See, this is a construction of a Königsberg bridge problem with the 7 edges. This is a very, very interesting problem. See, between land area is given as A, the land area in this side is given as C, land area in the lower side is given as B. Similarly, land area between these two bridges is connected as D. So these land portions are converted to a graphical structure. See, the land portions are taken as the vertices and the bridges between the land portions are taken as the edges. So this is an interesting problem in graph theory where the Königsberg bridge problem exists and Königsberg bridge is there with 7 bridges. The problem is that starting from one particular bridge, can a person travel to all the bridges exactly once and come back to the starting point? So starting from a particular bridge, traveling through all the edges, all the bridges, can a particular person come back to the starting point? This is an interesting question which arises from the Königsberg bridge problem. That is that, suppose I am starting from the point B, can I pass through all the edges exactly once and come back to the starting point B? Suppose I am taking the starting point to be B, I have to travel each and every edge exactly once and I am coming back to the same point B. So a bridge problem is converted to a graphical problem. The solution to this problem was given by Euler. So that becomes the Eulerian graph, and Euler tour is a tour which travels each edge exactly once. A graph is Eulerian if it contains an Euler tour. A graph is said to be Eulerian if and only if it has no vertices of odd degree. See here, in this graph, there are 2 vertices with odd degree. So see here, C is a graph with the degree 3. D is a graph with the degree 3. Similarly, B is a graph with the degree 3. A is a graph with the degree 3. Eulerian graph will never have a vertex with the odd degree. So this graph is not an Eulerian graph. So the answer for the Königsberg's bridge problem is that starting from a particular point, we cannot come back to the same point. Starting from a particular point, we cannot traveling through all the edges. I cannot come back to the same point. So starting from this point B, traveling through all the edges, I cannot return back to B. This is given by Eulerian graph. See the graph over here. In this graph, the degree of each and every vertex is even. Here the degree is 4, degree is 4, degree is 4, degree is 4. In this vertex, degree is 2. So this graph is an Eulerian graph. This graph cannot be an Eulerian graph because this vertex is of degree 3. So solution to the Königsberg bridge problem is the graph is be Eulerian. This concept of conical bridge problem can be applied to the Chinese postman problem. So what does a postman do? A postman want to pick up all the mail from the post office. He have to travel to all the streets, and he had to come back to the post office in order to return the remaining mails. So this is the main job of postman, and this problem can be solved by using the concept of Eulerian graph. See, from a particular vertex A, the postman can go to B, then he can travel to C, he can travel to D, come back again to E, F, again to C, E, B, F, A, so that the total weight is 43. If he chooses a path in this way, the postman has to move a very smallest distance to cover all the areas in his street. So in a weighted graph, Chinese postman problem is just that of finding a minimum weight tour in a weighted connected graph with non-negative weights. Next, check the graphs for Eulerian. This is an work for you. Students, you can take up these graphs in your note, and you can check for Eulerian. Starting from a particular point 1. You have to move through all the edges exactly once and come back to the same point 1. So this graphs you must have played during the small ages. Starting from a particular point, can we move through all the edges exactly once and come back to the same point? You can check these graphs for Eulerian or not. You can draw out these, you can check out these graphs in your note, and you can have an interesting game over here. And next comes the concept of dominating set. So in a graph theory, a dominating set is an interesting concept. The name itself says that a dominating set is really a dominating set which is adjacent to the remaining members. So see, in a graph theory, for a graph G, I'm going to find out a subset D of V such that every vertex not in D is adjacent to at least one member of D. So in order to choose and representative, you can use the dominating set. See, here there is a graph with the 6 vertices. A is a graph with the 6 vertices. B is also the same graph. C is also the same graph. I am choosing some representatives in this graph. See, I have chosen 3 representatives because these 3 vertices are adjacent to the remaining vertices. In the second graph B, I have chosen 2 representatives. So these 2 representatives are adjacent to the remaining vertices. Similarly, in the graph C, I have chosen 2 representatives. So this is an example of a dominating set. Domination number is the number of vertices in the smaller dominating set. So A is also A shown with the red is also a dominating set. B shown with the red vertices is also a dominating set. C shown with the red vertices is also a dominating set, but the minimum dominating number is 2. See the dominating queens in a chessboard. So it is an interesting application. So in the chessboard, you must have understand the movement of a queen. A queen demolishes all the persons in his line horizontally, vertically, and diagonally. See, a queen has a power to demolish all the other coins which are present in the horizontally, vertically, and even diagonally. See, I have placed some 5 queens in some interesting positions. If I place these queens in this position, all the remaining chess pieces get damaged. See, this queen will demolish the coins in this position, at this position together with this position. Similarly, the queen placed in this position will demolish all the other pieces in this position. This queen piece will demolish here diagonally and also diagonally upwards. This queen will demolish all the chess pieces in this position. Also, finally, the last queen will demolish. These 5 queens are enough to demolish all the chess pieces in this position. So finally, there comes a total domination. A total domination is also a interesting concept in dominating set. See here, I have given you an example to differentiate what is a dominating set and total dominating set. So dominating set means if I choose 2 and 5, it will be enough. For dominating set, if I choose 2 and 5, it will be enough, because 5 is adjacent to 4, 5 is adjacent to 6, 5 is adjacent to 1, 5 is adjacent to 3. In order to choose 2, I am choosing 2. But total dominating set means a set in which we have to choose in such a way that the remaining vertices must also be adjacent. So the vertices inside the dominating set should also be adjacent. A set S of vertices in the graph is called total dominating set if for every V belonging to V there exists a vertex such that U is adjacent to V. See, if you can see clearly in this example, 2 and 5 can be considered as a dominating set with the domination number 2. But for total dominating set, the members inside the set must be adjacent. So 4, 5, 6 is taken as a total dominating set. Application of domination and total domination. See, in companies, in order to choose a committee, they are using the concept of domination and total domination. So I can choose 2 types of committees. See, A is a committee with the persons 1, 2, and 9. See, A is a committee with the persons 1, 2, and 9. But there is no link between 1, 2, and 9. That is, there is no friendship or there is no understanding between these 3 persons. 1, 2, and 9 are independent persons. So I'm choosing a committee in such a way that committee members must not be known to each other. In this way, I can use the concept of a domination. Similarly, I have chosen another set called as B. See, I have chosen another set called as B, where B is 10, 4, 8, and 6. And in this is the concept of total domination. In this set, these 4 members are interlinked with each other. They are interlinked with each other. So in the committee A, the persons 1, 2, 9 are not interlinked, they are not related to each other. But in committee B, I have chosen some 4 persons, but these 4 persons have some understanding with each other. 4 has some understanding with the 10, 9 has some understanding with the 10, 8 has understanding with 10, etc. So in order to choose a committee of persons in companies or in colleges or in somewhere, you can use the concept of domination and total domination. This concept of total domination is applied in school bus routing. So in school bus, no child entering the school bus from their houses shall have to walk farther than 1/4 miles. The student should not walk more than 1/4 miles to the bus pickup point. So this concept of total domination is applied to find out the school bus routing. So another interesting concept in graph theory is the graph coloring, and this is the final concept in graph. So this graph coloring is a procedure of assignment of colors to each vertex of a graph G such that no adjacent vertices get the same color. See the graph here. I am giving the colors to this graph in such a way that no 2 adjacent vertices get the same color. See, these 2 vertices are adjacent, but these 2 vertices does not get the same color. So objective of this is to minimize the number of colors while coloring the graph. The objective of the graph coloring is to minimize the number of colors. So the smallest number of colors required to color a graph is called as a chromatic number. So in this graph, the chromatic number is 3 because I have used only 3 colors, green, blue, and red. So the minimum number of colors required to color the vertices of a graph is called as the chromatic number of a graph. And this concept of chromatic number is used to solve the Sudoku problem. So you must have gone through Sudoku problem in newspapers. You must have played these games using 9x checkerboard. And this concept of Sudoku can be applied using graph coloring. See, I have taken a 4x4 Sudoku problem. See, I have converted this problem to a graph theoretical problem. See here, in a 4x4 checkerboard, there are 16 squares. So I am numbering the squares as 1, 2, 3, 4, 5, 6, etc. up to 16. For each of these 16 numbers, I have placed 16 vertices. So in a Sudoku 4x4 checkerboard, I am naming all the vertices from 1 to 16. After naming these 16 vertices, I am going 16 numbers. I have placed 16 vertices for each of these square boxes. Next, I am going to connect the edges in such a way that 1 is adjacent to 2, 1 is adjacent to 3, 1 is adjacent to 4 because 1 lies horizontally with 2, 3 and 4. Similarly, 1 lies horizontally with 5, 9 and 13. So in the next picture, see, I am going to draw an edge between 1, 2, 1, 3, 1, 4, 1, 5, 1, 9 and 1, 13. So 1 I have connected with all the remaining. So the color which I give to 1 must not be given to 5, must not be given to 9, must not be given to 13. So the color which I am given to 1 can be given to 6 or 7 or 8 or 10, 11, 12, etc. In the similar way, you can go for 2 also. For the vertex 2, I am going to connect with 1, 3, 4, 6, 10, 14. The color which I given to 2 cannot be given to these vertices. The remaining vertices can get the color of 2. Similarly, we can try it for 3, we can try it for 4, we can try it for 5, 6, 7, 8, 9, etc. So this graph will be in such a way. So 1 is connected to 2, 3, 4, 5, 9 and 13. 2 is connected to etc. And 3 is connected with the remaining vertices. 4 is connected with the remaining vertices. Now I have depicted the color for each of the vertices. See, 1, the color 1 cannot be given to 2, 3, 4. The color 1 is given to 7. The color 1 is given to 12. The color representing 1 is given to 14. In similarly, 2 is given blue color. 2 cannot be given to 3. 2 cannot be given to 4. So similarly, 2 cannot be given to 6, etc. So the color blue is given to 8. Color blue is given to 9. And color blue is given to 15. Similarly, the color yellow is given to 3, 5, 10 and 16. The color 4 is given to color black is given to 4, 6, 11 and 13. So after giving coloring to these edges, I color the same to the 16 square boxes. See, the square box with 1 gets red, with 2 gets blue, with 3 gets yellow, with 4 gets black. Similarly, the square box with 5 gets yellow, with 6 gets black, with 7 gets red, and you can give the numbers as such. Red boxes can be filled with 1, blue boxes can be filled with 2, and similarly, yellow boxes can be filled with 3, and finally, black boxes can be filled with 4. This is the way of solving a Sudoku problem using graph coloring. So similarly, edge coloring can be used in scheduling of games. So similarly, as giving vertex coloring, edge coloring also giving colors to edges so that no two adjacent edges gets the same color. See here, this is an example of an edge coloring. So adjacent edges do not get the same color. I have used 3 colors. One is purple, next one is blue, and next one is brown. I have used 3 colors to depict the edge coloring. See here, there are 5 persons. 1, 2, 3, 4, 5. This edge coloring concept can be applied to schedule the matches between these 5 persons. See here, there is a color with purple, there is a color with blue, there is a color with green, and there's a color with black. Purple matches can be done in the first day. So that is between 1, 5 and 2, 4. Green matches can be done in the second day. That is between 5, 4 and 1, 3. A blue match can be done between 1, 4 and 2, 3. And similarly, black matches can be done on the day 4th day. So in this way, we can schedule the games between some 5 persons. So graph coloring is applicable in Sudoku game. Edge coloring is applicable in sports scheduling. And the graph coloring of faces. See, suppose I am drawing a map. I can choose each face of the map as a particular color, and I can convert that face map of the color to a vertex in this way. For each red color, I have depicted a vertex with red color, blue color, red color, yellow color, etc. And this becomes the graph coloring of faces. The idea of coloring the faces of a map is to assign each face color of the graph a color in such a way that 2 faces get different colors. This coloring of map is called as 4-coloring theorem. The 4-color map theorem states that for any map, we can just use 4 colors to color the map. See here, they have used only the 4 colors of red, orange, blue, and yellow for coloring the map of Germany. So for coloring the map, we can use just 4 colors, and this is known as the 4-color theorem. And finally, there is a interesting crazy cube problem of a coloring. So here, see here. Here I have taken some of the 4 cubes and I am depicting this 4 cube into a multigraph. See, blue is opposite to white. Green is opposite to red. Similarly, white is opposite to green. If the colors is opposite, I can mark an edge. Similarly, green is opposite to green. Red is opposite to blue. See here, blue is opposite to red. I am marking an edge. Blue is opposite to white. I am marking an edge. And similarly, blue is opposite to red. I am marking an edge. And all these cubes are converted to graphs. And finally, this graph network is given as a multi-graph using the coloring concept. So a cube can be converted, crazy cubes can be converted to a multi-graph using the coloring concepts. Thank you, students. If any questions is there, you can ask me. With this, I stop my presentation.
No, ma'am, no questions.
Okay, ma'am. Thank you, ma'am.
Thank you, ma'am, for expounding so many beneficial applications. It immensely satisfies our curiosity towards graph theory. Really fortunate to have you here, ma'am.
Thank you so much.
Feedback link will be provided in the chat box. Kindly fill it and receive the e-certificate.
No duty is urgent than that of returning thanks. Now I call upon Ms. R.M.C. Ashni of First MSc Max to present the vote of thanks.
Good afternoon to all. I deem it a great honor and privilege to propose the vote of thanks on this memorable occasion. Let me first of all start by giving glory to the Almighty God for making today's occasion an resounding success. First and foremost, I thank both of our chief guests, Dr. P. Chitra Devi, who spoke on the topic A Glimpse on Decomposition of Graphs, and Dr. A. Rizwana, who took the topic Real-Life Applications of Graph Theory. They, despite their busy schedule, has found to grace this occasion. Thank you, ma'am. I am grateful to the organizing secretaries, Dr. S. Kavita and Mrs. Afina Rezalayan, who organized this webinar. Thank you, ma'am. My heartfelt thanks to all the staffs for their valuable contribution and guidance. Finally, I thank all the students and participants of other college for your cooperation in making this function a great success. Once again, I thank all for your attention. Thank you.
Thank you, girls. Thank you, girls, for all your cooperation and wonderful listening. I hope that this session will be a great inspiration for all of us. Thank you all.
Thank you,
Thank
ma'am.
you, students. Thank you, students.